There is a star out there, somewhere in the infinite stretches of the cosmos, that refuses to follow the rules. It burns, it shines, it lives, and like all stars, it begins to collapse under its own weight. But unlike others, it doesn't end in a supernova, nor does it vanish into the oblivion of a black hole. Instead, it collapses forever. Trapped in a slow-motion fall through time, this star exists at the brink of death yet never truly dies. It never reaches the finish line. It is an enigma, a cosmic phantom eternally spiraling inward, without ever crossing the final threshold. What if we've misunderstood the death of stars all along? What if not all stellar corpses become black holes, and instead, some enter a limbo of endless collapse? This is the hauntingly beautiful proposition of eternally collapsing objects, or ECOs. They challenge the very fabric of our understanding of gravity, space, and time. They refuse to be defined by the conventional rules of stellar evolution. These objects might exist just outside our current reach of detection, so similar to black holes that we mistake them for one, but fundamentally different in a way that changes everything. In a universe obsessed with beginnings and endings, ECOs exist in the haunting space in between. But before we continue, subscribe to the channel so you don't miss out on any of these videos. Imagine a star so massive that its own gravity starts pulling it inward once nuclear fusion halts. Normally, we expect this story to end in one of two ways: a neutron star if the collapse is halted by neutron degeneracy pressure, or a black hole if gravity wins entirely. But ECOs rewrite this narrative. They tease the border of becoming a black hole, collapsing ever so slowly, nearing the event horizon, yet never quite getting there. As far as the laws of physics and the eye of an outside observer are concerned, they could continue collapsing for eternity, never forming a singularity, never sealing themselves off from the universe, and never vanishing completely from view. And that's where the fascination begins. What does it mean for a star to never die? Could this be the key to resolving the greatest paradoxes in theoretical physics, like the infamous black hole information loss problem? Could it be that our observations of black holes are not what we think? What if we've been staring at ECOs all along? These stars, if they exist, aren't just a curious exception. They would represent a new category of celestial object, governed by a different cosmic logic. They would stand as bridges between our universe and a realm beyond time. A place where gravity almost, but never quite, wins. A place where death is indefinitely postponed. This mystery, this paradox, this refusal to die, makes ECOs one of the most compelling frontiers in astrophysics. They are the immortal stars of the universe. They collapse, but they never disappear. They challenge black holes, and in doing so, challenge us to rethink what we believe about the fabric of reality itself. Every star is born with a countdown, ticking quietly in the background of its life. Fueled by the fusion of lighter elements into heavier ones, stars shine brilliantly for millions or even billions of years, balancing the inward pull of gravity with the outward push of radiation. But this delicate equilibrium is temporary. Eventually, the fuel runs out. Hydrogen becomes helium, helium becomes carbon, and the chain continues until iron, the fusion dead end, is formed. Beyond this point, no more energy can be extracted through fusion. Gravity, relentless and patient, begins to take over. In lower mass stars like our Sun, this collapse is gentle. The outer layers puff off, forming a glowing planetary nebula, while the core shrinks into a dense white dwarf. If the star is more massive, the collapse continues into a neutron star, an object so dense that a teaspoon of it would weigh more than a mountain. But even this is not the final act for the heaviest stars. For those, gravity doesn't stop at neutron degeneracy pressure. It crushes the star further, until, according to the traditional view, the core collapses into a singularity, a point of infinite density wrapped in an event horizon, the black hole. From the outside, the collapse seems to happen quickly, the star disappearing behind its own gravitational shadow. Beyond that point, nothing, not even light, can escape. It becomes a ghost in the cosmos, visible only by its indirect effects. This is the familiar story of stellar death. An elegant, if terrifying, endgame dictated by Einstein's equations and the limits of known physics. But what if that final act never actually plays out? What if the curtain falls just before the singularity takes the stage? That's the unsettling idea posed by eternally collapsing objects. ECOs suggest a cosmic twist in this script. When a massive star exhausts its fuel, it does indeed begin to collapse. But instead of sealing itself off behind an event horizon, the collapse slows. Not because it stops, but because of something far stranger, it becomes asymptotic. The surface of the object keeps falling inward, inching ever closer to the Schwarzschild radius, the theoretical boundary where an event horizon would form, but never quite reaching it. To an outside observer, this process looks frozen in time. The light escaping from near the object becomes redder and fainter, time seems to stretch, and the collapsing surface appears to halt just above the brink. It's not that the collapse ends, it's that from our point of view, it might as well be eternal. This changes everything. In the conventional black hole picture, there is a point of no return. A boundary from which escape is impossible, and where all information is lost. But in the case of ECOs, that boundary never forms. There's no sealed-off region of spacetime. Instead, the object remains visible, faint, redshifted, and enigmatic. It's as if the star refuses to die. Caught in a kind of gravitational purgatory, it collapses endlessly but never quite disappears. This distinction is subtle, but fundamental. Instead of being devoured by a singularity, the matter that once formed a living star becomes a permanently collapsing, slowly radiating shell that defies finality. Where black holes promise obliteration and silence, ECOs suggest a prolonged, whispering presence. Instead of an event horizon sealing off the universe from their secrets, ECOs remain just shy of that boundary, always almost gone, but not quite. They challenge the idea that gravity always wins completely, and they offer a radical possibility, that death, in the stellar sense, might not be absolute. The black hole has long reigned as one of the most iconic and mysterious predictions of general relativity. It's the cosmic enigma that captures both the public imagination and the attention of physicists, a region of spacetime where gravity is so overwhelming that nothing, not even light, can escape. In this traditional view, a black hole is defined by its event horizon, the point beyond which the universe loses track of information. Once something crosses that invisible boundary, it's gone, permanently severed from causal contact with the rest of reality. At the center lies a singularity, a point of infinite density and zero volume, where the known laws of physics collapse into mathematical nonsense. This singularity, surrounded by the event horizon, is completely hidden from view. The outer horizon becomes the only observable feature, and anything inside it is doomed to fall inward, ultimately crushed by an infinitely curved fabric of space-time. This model, as haunting as it is beautiful, comes straight from the mathematical heart of Einstein's field equations. It has been refined, debated, and generally accepted by the astrophysical community for decades. It explains many observations, gravitational lensing, the movement of stars near invisible points in space, and even gravitational waves from merging objects. But beneath the surface, the standard black hole model carries some deep, unresolved paradoxes. And this is where eternally collapsing objects step in. ECOs challenge the very foundation of what we believe black holes to be. They propose that perhaps our interpretation of the mathematics has gone awry. Instead of accepting that singularities and event horizons are physical realities, ECO theorists argue that they might be artifacts, idealized endpoints that are never actually reached in nature. From a distance, an ECO can look remarkably similar to a black hole. It's compact, dark, and massive. But the key difference lies in what we believe happens during and after the collapse. In the standard model, the collapsing star disappears behind the event horizon in finite time from its own reference frame. But to an outside observer, time near the event horizon slows to a crawl, becoming infinitely dilated. The object appears frozen just above the horizon, never quite vanishing. ECOs take this observational perspective and elevate it to physical reality. They argue that what we see, this eternal, slow-motion collapse, isn't just a visual illusion caused by relativity. It is, in fact, the true fate of the collapsing star. The event horizon never forms. The singularity is never created. Instead, the collapse proceeds forever, asymptotically approaching, but never reaching, the critical threshold. The star becomes an eternal performer in a cosmic illusion, forever nearing death but never passing through it. This reinterpretation reopens doors that black holes had closed. Without a true event horizon, information might not be lost. Without a singularity, we may not need to discard the laws of physics. ECOs provide a stage on which the most troubling paradoxes of black holes, especially the information paradox, can be addressed in a new light. They also redefine what it means to observe a black hole. If we are always seeing a collapsing surface hovering just outside the event horizon, then perhaps we've never truly seen a black hole at all, only the illusion of one. ECOs suggest that what we interpret as black holes could be mirages born from the extreme time dilation of collapsing matter. A shell of radiation and mass that spirals inward forever, giving the illusion of disappearance without ever actually achieving it. So the myth of the black hole, as ECO proponents might put it, is not that these objects don't exist, but that they may not exist in the way we've long believed. The black hole may be less of a cosmic prison and more of a horizonless abyss, open, evolving, and eternally unfinished. At its core, an eternally collapsing object, an ECO, is a bold alternative to one of the most accepted ideas in astrophysics. It offers a fundamentally different view of what happens to massive stars when they die, stepping outside the boundaries of mainstream black hole theory and asking, what if collapse never actually completes? An ECO is exactly what its name suggests, an object that collapses forever. But this isn't just poetic metaphor, it's a literal interpretation of what happens when gravity pulls matter inward without ever allowing that matter to cross a final, irreversible boundary. The collapse continues indefinitely, never culminating in a singularity, or sealing itself behind an event horizon. To understand ECOs, we need to revisit the process of gravitational collapse. When a massive star exhausts its fuel, the internal pressure that once resisted gravity vanishes. The star's core starts to contract. For stars beyond a certain mass threshold, this contraction becomes unstoppable, or so the standard black hole model would claim. But in the ECO framework, a critical twist emerges. The collapse slows down dramatically due to the buildup of internal radiation and relativistic effects. This radiation, produced from the immense heat and friction of collapsing matter, doesn't vanish. Instead, it becomes increasingly trapped inside the object. As matter compresses and temperatures skyrocket, radiation pressure builds within, opposing the pull of gravity. The result is a kind of dynamic equilibrium. Collapse continues, but at an ever-slowing rate. This resistance prevents the formation of an event horizon, the boundary beyond which light and information can never escape. Instead of forming a traditional black hole, the object evolves into a quasi-stable state, a surface that continues collapsing inward, but at a pace so slow it effectively freezes from the perspective of an external observer. The closer it gets to the Schwarzschild radius, the theoretical radius of a black hole, the slower the collapse appears. Time dilation becomes extreme, so much so that from our vantage point, the surface of the object seems to stall just above the horizon and never actually crosses it. This is the defining feature of an ECO. It's not simply a collapsed star, it's a forever collapsing star. Its outer layers appear frozen in time, while internally, radiation pressure and possibly quantum effects work to eternally slow the collapse. No event horizon forms. No singularity arises. And critically, no information is truly lost. Think of it like this. If a traditional black hole is a locked room with no doors or windows, an ECO is a room with walls so thick and dimly lit that you can barely see in, but the door is technically still open. Information may still escape, albeit in extremely redshifted and degraded form. It might take eons, but the universe hasn't completely lost access to what lies inside. ECOs, then, straddle a strange line between life and death, visibility and invisibility, collapse and stability. They exist just at the boundary of black hole territory, mimicking many of the outward signs of a black hole without ever taking that final plunge. From a distance, they may appear identical to a black hole, a compact, dark, supermassive object distorting the space around it. But fundamentally, they are different creatures. They are not voids from which nothing can return. They are not ends. They are processes, never finished, never halted, eternally in motion. This definition makes ECOs not only a theoretical curiosity, but also a powerful lens through which we can re-examine some of the deepest puzzles in modern physics. If ECOs are real, they reshape our understanding of gravity, time, and even the flow of information through the universe. They suggest that nature might abhor the finality of singularities, offering instead a universe that prefers infinite processes over abrupt boundaries. The idea of collapse without end feels paradoxical. After all, when we hear the word collapse, we think of a sudden, irreversible motion, a building falling, a wave crashing, a star imploding in the violent finale of its life. But in the case of eternally collapsing objects, the term collapse takes on a new, almost surreal meaning. It becomes a process not of rapid descent, but of eternal deceleration. The collapse happens, yes, but it never finishes. It continues forever, asymptotically approaching a conclusion that it can never quite reach. This infinite gravitational collapse begins just like any other. A massive star, having exhausted its nuclear fuel, loses the outward pressure that counteracted gravity. The core implodes, temperatures soar, densities rise, and the object contracts under its own immense mass. But here's where the ECO deviates from the classic script. The collapse, while initially rapid, begins to slow. Why would it slow? Because as matter falls inward, it compresses into an ever smaller volume, generating staggering amounts of heat and energy. This trapped energy, often in the form of radiation, photons, neutrinos, or even virtual particles, doesn't easily escape. Instead, it rebounds off the infalling matter, building pressure. This radiation pressure doesn't stop the collapse entirely, but it starts to resist it. It introduces a balancing force, one that can never fully counteract gravity, but can slow it enough to delay the end indefinitely. The deeper the object collapses, the stronger this internal resistance becomes. Add to this the intense warping of spacetime near the would-be event horizon, and you have a recipe for infinite delay. According to general relativity, time for a distant observer slows down as one watches something fall toward a gravitational source. Near the Schwarzschild radius, time stretches so profoundly that an outside viewer would see the object collapse in ever-slowing motion. The closer it gets to that critical radius, the more it appears to freeze. Not metaphorically, literally, from the viewpoint of an external observer, the motion becomes suspended in extreme time dilation. But internally, the object keeps moving. Its collapse continues. Not as a sudden freefall, but as an infinitesimal progression deeper into its own gravity well. This asymptotic descent is key to understanding ECOs. The surface of the object approaches the Schwarzschild radius, but crucially, never crosses it. Instead, it inches closer with each passing moment, always nearing, never reaching. If a black hole is an abrupt ending, an ECO is a mathematical whisper, a process caught between existence and non-existence, in a loop of constant but incomplete collapse. The physics behind this slowing collapse can be traced to the Einstein field equations themselves. Under extreme conditions, the equations allow for scenarios where the stress-energy tensor, the quantity that describes matter, energy, pressure, and momentum, doesn't simply lead to singularity formation, but instead to dynamic solutions where pressure and radiation stall collapse without ever truly stopping it. In these models, the gravitational pull remains, but the internal reactions push back just enough to keep the horizon at bay. It's a balancing act played on the edge of oblivion. Imagine standing at the edge of a cliff, leaning forward infinitesimally, each moment bringing you slightly closer to the edge, but never quite tipping you over. That's the trajectory of an ECO's surface. Every microsecond, it gets closer to the gravitational point of no return. But the very fabric of time and the buildup of radiation keep it suspended in this endless approach. This type of infinite collapse is not merely theoretical elegance. It has consequences. Without a horizon, there is no cutoff from the universe. Without a singularity, there is no place where physics breaks down entirely. Instead, you get an object that is, quite literally, becoming, never fully transformed, never fully collapsed, and never finished. This raises deeper questions. Can such an object radiate? Can it interact with the universe? Can it preserve information? All of these depend on the fundamental nature of this unending descent. ECOs don't just collapse, they do so forever, which means their story doesn't end. They don't reach a final state. They continue to evolve, infinitely slowly, straddling the border between what was once a star and what would otherwise have become a black hole. Collapse without end isn't just a theoretical oddity. It is a challenge to the idea that time, space, and gravity must always resolve themselves into singularities. It suggests a different kind of resolution, one that never actually resolves at all. As an object like an eternally collapsing object, ECO, continues its unending fall inward, there's another peculiar force at play: time itself. Near the surface of an ECO, time doesn't just slow down, it becomes so dramatically stretched that it nearly grinds to a halt. From our vantage point, the closer matter gets to this invisible, ever-approaching boundary, the more it appears to freeze. And not in the metaphorical sense. This isn't poetic license, it's a direct prediction of Einstein's general theory of relativity. To truly grasp how time behaves near an ECO, imagine observing a clock that's attached to the surface of this collapsing object. At first, the seconds tick by normally. But as the star collapses, drawing the clock closer and closer to the Schwarzschild radius, the radius at which a traditional black hole would form, something strange begins to happen. Each tick slows. The seconds become stretched. From the perspective of a distant observer, it starts to take longer and longer for each tick of the clock to occur. Eventually, those seconds turn into hours, then years, then millennia. The closer the collapsing object gets to forming a black hole, the more profound this time dilation becomes. In theory, when it reaches the Schwarzschild radius, time for that clock completely stops, as seen from the outside. But in the ECO scenario, the object never actually crosses this threshold. It merely dances infinitesimally above it, forever closing in, but never quite arriving. And because it never reaches that limit, the clock never truly stops. It just slows to such a glacial crawl that, for all practical purposes, it may as well be frozen. This is what physicists refer to as asymptotic time dilation. The collapse is infinite not only in space but also in time. The collapsing matter seems caught in a temporal web, forever suspended just above the point where a black hole would normally cut itself off from the universe. From within the ECO, time might seem to be flowing normally. Matter is still moving inward, radiation is still bouncing around, energy is still interacting. But to us, observers located far away from the intense gravitational grip, the entire process appears to unfold in slow motion. Slower than slow. Eternal. This paradox of motion without progress, of time that stretches toward infinity without actually reaching it, is not some fringe idea. It's built right into the very mathematics of general relativity. The equations governing time dilation near strong gravitational fields are clear. As you approach the Schwarzschild radius, time relative to an external observer dilates infinitely. That's not speculation, it's a well-understood consequence of space-time curvature. In the case of a black hole, we usually resolve this by saying that the infalling object crosses the event horizon in its own proper time. Its own clock continues ticking normally, while we, on the outside, simply can't see it cross because the light it emits becomes infinitely redshifted and delayed. It fades from view, never quite vanishing, but never quite observable again. This leads to the idea that the event horizon has been crossed, just not from our perspective. ECOs flip that interpretation. They take the outsider's view, the one we can observe, and make it the fundamental reality. They argue that what we see as infinite collapse might not be just an illusion of perspective. It could be a real, physical process. The surface of the ECO doesn't cross the Schwarzschild radius not just from our point of view, but from a deeper, objective perspective of space-time evolution. The extreme time dilation is not just an observational artifact, it is the defining feature of the object's very nature. This means that ECOs, while appearing frozen to us, are very much alive on the inside. Processes continue, radiation builds up, and feedback mechanisms persist. It is as if the object is trapped on the edge of a cosmic threshold, a temporal cliff it can never quite fall over. This idea radically redefines what it means to observe and measure events in extreme gravitational environments. For example, if an ECO emits light, or any form of radiation, that radiation must climb out of an extraordinarily steep gravitational well. As it does so, it loses energy, stretching out into longer and longer wavelengths. Eventually, it becomes so redshifted that it's barely distinguishable from the background noise of the universe. But crucially, it's still there. It hasn't disappeared completely. And if we had sensitive enough instruments and enough patience, we could, in theory, detect it. This opens up a major difference between ECOs and black holes. In the black hole model, the event horizon creates an absolute boundary, and information that crosses it is forever lost to the universe. In the ECO model, the lack of a true horizon means that information may remain accessible, buried beneath layers of redshifted radiation and time dilation, but not erased from the cosmos. It's almost as though the ECO exists in a different temporal frame than the rest of the universe. While galaxies spin, stars explode, and civilizations rise and fall, the ECO continues its inward spiral at a pace so slow, so imperceptible, that it feels timeless. It's an object that exists in real time internally, but is disconnected from the rhythms of external space-time. A temporal orphan. A star that lingers at the edge of death, caught in an endless fall that never concludes. This phenomenon isn't entirely alien to us. Time dilation, after all, is something we can measure here on Earth. Satellites in orbit experience time slightly differently from people on the ground due to gravitational time dilation. Our GPS systems have to account for it to stay accurate. Now scale that difference up to 1,000,000-fold, 1,000,000,000-fold, and you begin to glimpse what happens near the surface of an ECO. It's not a break in the laws of physics, it's a natural extension of them into the most extreme regimes. The consequence is both awe-inspiring and unsettling. We could be looking at what appears to be a static point in space, an unchanging black dot surrounded by dust and radiation, and never realize that beneath its skin, a massive stellar corpse is collapsing in eternal motion, light years away and thousands of years out of phase with our own temporal experience. This time trap creates a profound observational problem. If ECOs behave like this, how could we distinguish them from black holes? From our perspective, both would appear as dark, compact objects emitting little to no visible radiation, surrounded perhaps by accretion disks and gravitationally influencing nearby matter. But the key difference, the presence or absence of an event horizon, would be buried beneath layers of cosmic time. And yet, the idea persists, tempting physicists and cosmologists to look deeper, to question whether the things we call black holes are actually something more subtle, more elegant, and more temporally exotic. ECOs suggest a universe that doesn't cut off stories abruptly, but instead stretches them indefinitely, where endings are replaced by eternal processes, and where time itself becomes a player in the grand dance of collapse. If an object collapses forever, as in the case of an eternally collapsing object ECO, then the natural question arises, why doesn't it ever form an event horizon? According to the standard model of black holes, a sufficiently massive star collapsing under its own gravity will inevitably reach a point where its escape velocity exceeds the speed of light, creating a boundary from which nothing can return, the event horizon. But ECOs defy this fate. They avoid this critical threshold, not by stopping the collapse, but by orchestrating a delicate balance of internal forces, radiation pressure, quantum effects, and space-time dynamics, that indefinitely delay the formation of the horizon itself. To understand this strange defiance, we first need to consider what it takes for an event horizon to form. The Schwarzschild radius defines the radius at which the escape velocity equals the speed of light. Once collapsing matter crosses this invisible line, the surrounding space-time curves so intensely that nothing, not even light, can escape its grip. In classical general relativity, if nothing interferes with the collapse, this point is reached in finite proper time from the perspective of the infalling matter. But the external observer never actually sees this happen. Instead, the collapsing matter seems to freeze just above the horizon, becoming increasingly redshifted and dim. From the outside, it appears suspended at the brink of disappearance. Now, in standard black hole physics, this visual freezing is treated as an optical illusion. The event horizon does form, even though we never directly observe it. But ECO theorists propose something radical. What if this infinite time dilation isn't just a trick of perception? What if it reflects a deeper physical truth, one that fundamentally prevents the horizon from forming? This is where radiation pressure enters the scene. During collapse, especially in the final stages near the Schwarzschild radius, matter becomes compressed to such extremes that it begins emitting vast amounts of radiation. These photons, born in a gravitational well, struggle to escape. Many are trapped, bouncing within the collapsing structure, creating an immense buildup of internal radiation pressure. This pressure doesn't reverse the collapse. It's not strong enough to counteract gravity entirely, but it applies a brake, a constant push that slows the infall more and more as the density increases. The closer the object gets to the Schwarzschild radius, the more pronounced this resistance becomes. Because the gravitational redshift also intensifies, the escaping radiation becomes increasingly weak from an external perspective. But within the object, the radiation density rises dramatically. It exerts an outward force, not sufficient to cause expansion, but enough to drag the collapse into an ever-slowing spiral. Instead of free-falling into a singularity, the collapsing layers descend through molasses made of their own trapped light. This phenomenon is sometimes described using the concept of radiation trapping surfaces. These are boundaries inside the collapsing star where the gravitational pull is so strong that light cannot escape in the traditional sense. But these aren't event horizons, because they don't sever causal connections with the universe. They are more like fuzzy layers of delay, where light is imprisoned long enough to influence the dynamics of the collapse. But radiation isn't the only player at work. As the densities and energies approach extreme values, quantum effects begin to rear their head. Although we lack a complete theory of quantum gravity, there are several hints from semi-classical physics that quantum fluctuations may intervene to alter the fate of collapsing matter. Quantum field theory in curved spacetime, particularly the concept of Hawking radiation, already predicts that black holes are not truly black. They emit faint radiation due to virtual particle pairs forming near the event horizon. This quantum leakage suggests that the classical event horizon is not an impervious wall, but a probabilistic, thermodynamic surface. ECOs take this further. Instead of a fully formed event horizon radiating over time, they propose that quantum effects act preemptively. The intense buildup of quantum vacuum energy, particle creation, and radiation feedback prevents the actual formation of the horizon in the first place. This creates a kind of standoff, gravity pulling inward, quantum fields pushing outward, and radiation acting as a feedback loop to stabilize the balance. The result? An object that appears to flirt endlessly with the horizon but never consummates the formation. This scenario is not without precedent. In fact, there are parallels in other areas of physics, such as asymptotic states and dynamical systems, where variables approach a limit but never reach it in finite time. ECOs are gravitational asymptotes. They are what happens when nature resists absolute collapse, choosing instead a never-ending approach toward a boundary that remains forever just out of reach. Additionally, some ECO models incorporate mechanisms like quantum gravitational pressure, hypothetical effects that emerge from yet-to-be-fully realized theories such as loop quantum gravity or string theory. In these models, space and time themselves may possess discrete or quantized structures that resist being compressed into a singularity. The event horizon, being a geometric boundary in spacetime, might be incompatible with such granular structures. Instead, the collapse halts, or more precisely, becomes eternally sluggish, at a microscopic scale just above the horizon threshold. This has profound implications. If ECOs truly lack an event horizon, then the universe is never completely severed from their contents. Light, matter, and information, while greatly redshifted and delayed, can, in principle, still escape. This offers a tantalizing potential solution to the black hole information paradox. Since no horizon ever forms, there is no absolute loss of information. The collapsing star, though slow and faint, still speaks to the universe. Its story is not one of silence, but of eternal whispering. It's important to clarify, ECOs don't deny the immense gravitational pull or compactness of these objects. In fact, they agree with most black hole properties from a distance. An ECO would still bend light, tug on nearby stars, and create accretion disks that shine in X-rays. But the devil is in the details. If we could probe deeply enough into the timing of emitted radiation, or the subtle shifts in gravitational wave echoes, we might detect the absence of a true event horizon. That's the experimental hope, that somewhere in the ultra-faint signals of the cosmos, the missing horizon will reveal itself not through its presence, but through its persistent absence. In this light, the ECO is not just a theoretical oddity, it is a candidate for a more physically realistic object than the idealized black hole. It honors the equations of general relativity, respects the constraints of quantum mechanics, and does so without requiring the physics-defying singularity or the metaphysical vanishing act of the event horizon. So, why no event horizon? Because the collapse never finishes. Because radiation never stops pushing back. Because quantum effects refuse to be ignored. The ECO lives forever on the edge of gravitational oblivion, a monument to incompleteness. It is a cosmic question mark written into the fabric of space-time itself. When a massive star nears the end of its life, it prepares for one of the most dramatic transformations in the cosmos. For millions of years, it has fused hydrogen into helium, then heavier elements, building an iron core deep within. But fusion stops at iron. Fusing iron consumes more energy than it releases. With the outward pressure of fusion gone, the core collapses under its own immense gravity. The outer layers fall inward, then rebound in a titanic explosion, the supernova. This is where the story is supposed to split along well-established lines. For stars of modest mass, the collapse is halted by neutron degeneracy pressure, leaving behind a neutron star, a dense, city-sized remnant. But for the most massive stars, the collapse is too strong. Even the pressure from tightly packed neutrons cannot resist it. Gravity continues to crush the core inward, and according to traditional models, it passes the Schwarzschild radius, forming a black hole. That's the textbook version. A star dies in fire, and its heart is buried behind an event horizon. But ECOs offer a different ending, or rather, an ending that never quite ends. Let's rewind the clock and imagine that same massive star on the verge of supernova. The collapse begins. The core implodes, densities skyrocket, and for a moment, gravity seems unbeatable. But something subtle, something extraordinary begins to happen amid the inferno. As the core becomes increasingly compressed, the temperature inside soars to billions of degrees. Photons and neutrinos explode outward from the dense center. However, instead of escaping, a significant portion of this radiation becomes trapped by the intense gravity. It begins to push back. This trapped radiation acts as a buffer, a kind of invisible scaffolding that slows the collapse. As more matter piles onto the shrinking core, radiation pressure increases, not enough to reverse the collapse entirely, but just enough to delay it. The gravitational compression and the radiation rebound engage in a cosmic tug-of-war, transforming the collapse into an asymptotic process. The core doesn't become a black hole. It becomes an ECO. This transformation is subtle. From a distance, the collapsing object behaves almost identically to a nascent black hole. It continues to shrink, and the light emitted from its surface becomes more and more redshifted. Eventually, to an external observer, it seems to freeze just above the event horizon. But the crucial difference is that it never actually crosses the threshold. The event horizon, the signature feature of a black hole, never forms. The ECO, caught in eternal freefall, remains suspended in an endless process of becoming. What makes this scenario so compelling is that the transition from supernova to ECO doesn't require exotic new physics, at least not entirely. The ingredients are already present: gravitational collapse, radiation pressure, and the extreme conditions that form during core implosion. In fact, some models suggest that radiation pressure alone, when enhanced by relativistic time dilation and feedback, can delay the collapse indefinitely. There's even reason to believe that supernova explosions themselves might help facilitate ECO formation. In traditional black hole formation, the supernova might not be powerful enough to expel all of the outer layers, and the star's remnants fall back inward, contributing to the final collapse. But if radiation builds up quickly during the implosion phase, and time dilation becomes significant early enough, the star's core might become trapped in a state where infalling matter accumulates more slowly and collapses more gradually, reinforcing the ECO's development. It's as though the supernova sets the stage, but instead of ending the star's life with finality, it leaves behind a glowing ember that never quite fades. A star caught in suspense. An eternal process ignited by death, but never concluding in singularity. This perspective also reframes the aftermath of supernovae. In some cases, we see explosions but fail to identify the compact remnants they supposedly leave behind. Astronomers have long puzzled over missing black holes, remnants that should be detectable by their accretion behavior or gravitational effects, but that seem invisible or undetectable. ECOs might provide an answer. If these remnants never fully collapse, if they remain just above the horizon with minimal emission, they would be nearly indistinguishable from black holes at a distance. But they wouldn't be true black holes. They would be incomplete, eternal, and unfinished. This slow collapse also explains the observational difficulty in distinguishing ECOs from black holes. In the moments after a supernova, the object may look, from our perspective, like it has formed a black hole. But what we're actually seeing is the beginning of an eternal collapse, an object that will continue shrinking, radiating, and redshifting for trillions of years, never fully completing its transformation. There's even a poetic irony in this idea. A star dies in a violent supernova, the most energetic death in the universe, but the object it leaves behind does not truly die. It falls forever, locked in time, its energy dissipating over eternities, its surface forever shrinking but never vanishing. Its heartbeat slows but never stops. This eternal suspense, this unending finale, is what gives ECOs their eerie, almost ghost-like presence in astrophysical theory. They are not corpses like neutron stars, nor are they voids like black holes. They are processes, unresolved, liminal, suspended between states. Born in fire, destined to never rest. So, when a massive star reaches the end, it might not vanish. It might collapse into a state of perpetual becoming. A supernova may not be the final punctuation mark of a stellar life, but a comma, leading not to silence, but to a whisper that continues into cosmic eternity. The collapse of a massive star is a fierce and unstoppable force, at least, that's what we've long believed. Gravity, once unchallenged by the outward pressure of nuclear fusion, is assumed to take over completely, pulling every atom inward until nothing remains but a singularity hidden behind an event horizon. But in the eternally collapsing object ECO model, there's a surprising ally that rises from within the collapsing core itself: radiation. And not just as a fleeting flash of light, but as a long-lasting, decisive force capable of dragging an infinite collapse into slow motion. In fact, one of the key ideas behind ECOs is that radiation doesn't just escape, it gets trapped, and this trapping changes everything. Radiation in the form of photons, neutrinos, and other particles is always present during the gravitational collapse of a massive star. As densities rise and temperatures soar to billions of degrees, the collapsing core emits vast quantities of high-energy radiation. In a normal stellar environment, this radiation would escape into space. But when the collapse is so extreme that space-time itself curves sharply around the matter, escaping becomes harder and harder. The light doesn't flee, it loops, it spirals, it reflects inward. This is the beginning of the radiation trap. As the collapse progresses and the star's outer layers fall inward, the interior becomes so dense that even photons, which normally race through space at light speed, are repeatedly scattered and delayed. The radiation no longer escapes. It accumulates. And with that accumulation comes pressure. This trapped radiation begins to exert an outward force, radiation pressure, a phenomenon well understood in classical physics. In ordinary stars, it's radiation pressure that balances gravity during the star's lifetime, keeping it stable and allowing fusion to continue. But in the ECO scenario, this pressure takes on a new, more dramatic role. It becomes a brake that acts during the collapse itself. The tighter gravity pulls inward, the harder radiation pushes back. And unlike in a typical star, where balance is achieved, here the two forces don't cancel each other. They create an eternal imbalance that slows everything down forever. As collapse deepens, the radiation pressure doesn't stop the infall, it just slows it. This slowing is key. Instead of allowing the core to cross the Schwarzschild radius and form an event horizon, the increasing radiation pressure pushes the surface of the object closer and closer to that limit, but never allows it to cross. It's a kind of cosmic tug-of-war with no winner, only delay. Collapse is stretched out over infinite time, while the object's radius asymptotically approaches, but never breaches, the critical boundary. This is more than just a speculative concept. It's rooted in real physics. The Einstein field equations of general relativity allow for dynamic solutions where energy and momentum, represented in the stress-energy tensor, include contributions from radiation. When you factor in the presence of intense radiation trapped within a collapsing star, you get solutions where gravitational collapse doesn't culminate in a singularity, but is instead perpetually regulated by internal energy. The geometry of spacetime is altered, not enough to reverse the collapse, but enough to infinitely slow it. This radiation pressure becomes increasingly dominant the closer the star's surface gets to the Schwarzschild radius. In fact, due to the extreme gravitational redshift near that boundary, the radiation becomes more and more energetic from the perspective of the collapsing frame, despite appearing dim and cold from the outside. This strange inversion, where the inside is a furnace and the outside sees only darkness, contributes to the ECO's disguise as a black hole. There's also a feedback mechanism at work. As the collapse slows, radiation becomes even more trapped. As radiation becomes more trapped, pressure increases. As pressure increases, collapse slows further. This self-sustaining cycle is what allows the collapse to continue forever, asymptotically and eternally. The object never reaches the point of singularity or event horizon formation, not because collapse stops, but because it cannot accelerate fast enough to finish the job. This endless regulation by radiation has another extraordinary consequence: no horizon ever forms. Since the collapsing surface never dips below the critical radius, there is no region of spacetime that becomes causally disconnected from the rest of the universe. All information, no matter how delayed or redshifted, can in principle still make its way outward. This single fact has seismic implications for our understanding of black holes, information loss, and the ultimate fate of matter. It also subtly transforms how we should think about supernova remnants. After a massive explosion, when we believe a black hole has formed, we might instead be witnessing the birth of a radiation-regulated ECO. That object would be compact, dense, and nearly invisible, emitting only faint, heavily redshifted radiation over incredibly long time scales. To our instruments, it would look like a black hole. But in reality, it would be an object in a suspended state of collapse, eternally slowing, governed not by finality but by feedback. Quantum physics may also lend a helping hand here. While radiation pressure originates in classical thermodynamics and electromagnetism, quantum field theory suggests that even in vacuum, fluctuations produce energy and momentum. In extreme gravitational environments, these quantum effects could enhance the buildup of radiation pressure. Some models even suggest that quantum corrections to the Einstein equations could prevent horizon formation entirely. Another nail in the coffin for singularities, and a new life for eternally collapsing structures. To visualize this, imagine a rubber ball rolling down a hill. At first, it picks up speed. But halfway down, the hill begins to flatten, and the air grows thick with molasses. The ball continues rolling, slower and slower, never reaching the bottom. The steeper the hill was in the beginning, the more momentum it had. But the molasses, our metaphor for radiation pressure, only grows denser the farther the ball rolls. That's the fate of a star collapsing into an ECO. Its collapse continues forever, but is perpetually slowed by its own internal energy, its light, heat, and quantum whisperings, trapped inside a prison of its own gravity. This is what makes ECOs such haunting and fascinating objects. They are not frozen in time because they lack energy. They are frozen because they are overflowing with energy, so much so that their own brilliance becomes their own confinement. Trapped radiation becomes not just a byproduct of collapse, but the engine of its eternal slowing. So yes, radiation saves the day. Not by preventing collapse, not by reversing gravity, but by transmuting collapse into something endless. Something that lives at the threshold of death and never crosses it. A cosmic twilight, held forever by the light it cannot let go. From a distance, an eternally collapsing object, ECO, and a black hole might look nearly identical. Both are incredibly compact, exert tremendous gravitational influence on their surroundings, and can be the endpoints of massive stellar collapse. They both bend light, distort time, and pull in matter from nearby space. But underneath this superficial similarity lies a set of profound and foundational differences. Differences that speak not just to astrophysics, but to the very structure of reality. The differences between an ECO and a black hole touch on singularity formation, event horizons, radiation behavior, and the question that has haunted physicists for decades: does information disappear forever? Let's begin with the most iconic feature of a black hole, the singularity. According to classical general relativity, when a star collapses beyond the Schwarzschild radius, nothing can stop the gravitational crunch toward infinite density and zero volume. At the center of a black hole lies the singularity, a point where the known laws of physics break down, where space-time curvature becomes infinite, and where all matter is crushed into oblivion. This is not just a physical mystery, it's a crisis in the fabric of our equations. The singularity is a place where general relativity essentially throws up its hands and says, "I can't go any further." ECOs, by contrast, are defined precisely by the absence of a singularity. Because the collapse never finishes. Because radiation and quantum pressure slow the descent infinitely. The matter never reaches infinite density. Instead of everything collapsing into a single, infinitely compressed point, the interior structure of an ECO remains extended, albeit in an ultra-dense and time-stretched state. It may be unimaginably compact, but it is not infinitely small. The laws of physics may stretch, but they do not shatter. In this way, ECOs offer a vision of cosmic collapse that is dramatic, but still mathematically coherent and physically continuous. Next, we arrive at the event horizon, arguably the most famous and misunderstood feature of black holes. This boundary represents the point of no return. Anything that crosses it, including light, is irrevocably lost to the rest of the universe. The event horizon is not a material surface but a geometric boundary in spacetime, a line in the sand drawn by gravity itself. From the outside, infalling matter appears to slow down and fade away, but from its own frame of reference, it crosses the horizon in finite proper time, never to communicate with the outside again. ECOs, however, do not form an event horizon. The object gets arbitrarily close to the Schwarzschild radius, but never reaches or passes it. There is no true point of no return. The gravitational redshift becomes extreme, and time dilation becomes practically infinite, but causality is never broken. Information, energy, and matter can still, in principle, escape, albeit incredibly slowly and weakly. This distinction is not a minor technicality. It's the dividing line between an object that severs itself from the universe and one that remains, however faintly, a part of it. The absence of an event horizon is what allows ECOs to skirt around the biggest philosophical problems in black hole physics. Which brings us to radiation. Black holes, according to Stephen Hawking's groundbreaking work, do emit radiation due to quantum effects near the event horizon, so-called Hawking radiation. But this radiation is thermal, random, and carries no specific information about what fell into the black hole. It's like burning a library and trying to reconstruct the books from the ashes. Furthermore, Hawking radiation is incredibly weak, especially for stellar mass black holes. It's virtually impossible to detect with current technology. ECOs, on the other hand, may emit radiation in a very different manner. Because there is no event horizon, internal processes can still interact with the external universe. Radiation generated by trapped heat, quantum processes, and high-energy reactions inside the collapsing object may slowly leak out. This radiation is also highly redshifted and dim from our perspective, but unlike Hawking radiation, it might be non-thermal and information-rich. It may encode subtle details about the internal state of the ECO, details that are forever lost in the case of a true black hole. In this sense, ECOs could be talkative corpses, still whispering out clues about what's inside, even if those whispers take eons to be heard. This directly ties into the infamous information paradox. In the standard black hole model, information about matter that falls into the black hole is destroyed, or at least, rendered permanently inaccessible, when it crosses the event horizon. Hawking's original analysis implied that black hole evaporation leads to complete information loss, a violation of quantum theory's sacred principle that information is never destroyed. This paradox has led to decades of heated debate, speculative solutions like firewalls, holographic principles, and black hole complementarity. ECOs elegantly avoid the paradox altogether. Since no event horizon forms and no information is cut off, there is no violation of unitarity. Information is not lost, it's just trapped in a very deep and slow escape process. Over unimaginably long timescales, it may all come back, redshifted, delayed, and weakened, but intact. ECOs restore the cosmic accounting book. Nothing goes missing. The universe retains its memory. In many ways, the difference between black holes and ECOs is the difference between finality and continuity. Between silence and whisper. Between death as annihilation and death as transformation. ECOs aren't just alternative objects, they're alternative worldviews. They say that perhaps nature abhors true infinities. That instead of abrupt cutoffs, reality prefers soft boundaries, slow fades, and eternal processes. And perhaps, in the deepest reaches of space, where the oldest stars have collapsed and vanished from view, we are not surrounded by silent voids. Perhaps we are surrounded by the slow, flickering echoes of stars that never died. The idea of eternally collapsing objects is captivating, stars that collapse forever but never truly vanish, hanging in a gravitational limbo just shy of becoming black holes. But for all their theoretical elegance and philosophical allure, we must pause and ask a sobering question: are ECOs real, or are they just sophisticated mathematical mirages? Constructs that exist only in equations and speculation, but not in the heavens above. To understand whether ECOs could be real, we must begin by acknowledging that they are still, first and foremost, theoretical constructs. Unlike neutron stars or even black holes, whose existence has been strongly supported by observational data, from X-ray emissions, gravitational wave detections, and the iconic Event Horizon Telescope image, ECOs remain in the shadows. They haven't been directly observed. No astronomer has pointed a telescope at a candidate and proclaimed, with confidence, "This is an ECO." Instead, ECOs arise from the deeper tensions in theoretical physics. They were born not from empirical necessity, but from the desire to resolve paradoxes, to deal with the singularities and information loss problems inherent in black hole theory. In that sense, they are what theoretical physicists sometimes call constructive alternatives. They are not proposed to explain a missing signal, but to fill a conceptual hole in our understanding of extreme gravitational collapse. One of the primary drivers behind the ECO concept is the discomfort with singularities. When general relativity predicts that collapsing matter will compress into a point of infinite density, many physicists consider this a red flag, a sign that the theory is being pushed beyond its domain of validity. After all, infinities in physics are usually a warning that we're missing something, not a statement of physical reality. The singularity isn't a place, it's a failure of predictability. In this light, ECOs offer a way to sidestep the singularity problem. If the collapse slows down infinitely, it never reaches the conditions that create a singularity, and thus spacetime remains well-defined at every step. But does this make ECOs more real, or just more comfortable? That's a matter of interpretation. There are also compelling theoretical motivations beyond just the fear of infinities. ECOs naturally preserve information, a huge advantage when confronting the black hole information paradox. They don't require speculative fixes like holographic duality or firewalls. Their structure allows matter and information to remain in causal contact with the universe, albeit in an extremely redshifted and slow-dripping way. In this sense, ECOs seem to offer a more unitary, more quantum-compatible way to think about collapsed objects. Moreover, ECOs emerge as consistent solutions in general relativity when energy-momentum tensors include radiation, quantum pressure, or other non-vacuum effects. In other words, if you take Einstein's equations and account for all the stuff we know is present in a collapsing star, radiation, fields, heat, you can sometimes find solutions where collapse slows asymptotically, and no horizon forms. These are not whimsical thought experiments. They are grounded in well-understood mathematics. Still, theoretical possibility is not the same as physical necessity. Many solutions to Einstein's equations exist that have no known counterparts in the real universe. Wormholes, for example, can exist mathematically, but whether they exist physically is another matter entirely. So the burden remains: how do we determine if ECOs actually exist out there, rather than merely on paper? One major hurdle is observational indistinguishability. From a distance, ECOs and black holes behave almost identically. Their gravitational fields are practically the same. They warp spacetime in the same way, attract matter similarly, and produce nearly identical effects on nearby stars or gas. Even the radiation they emit, or fail to emit, can be indistinguishable without extremely precise instruments. This makes it extraordinarily difficult to confirm or refute their existence using current telescopes or detectors. The hope lies in subtle deviations. ECOs might produce different signatures in gravitational waves, perhaps in the post-merger echoes that follow black hole collisions. They might show minuscule differences in how they absorb or reflect high-energy particles. Or they might reveal their presence through ultra-slow emissions of non-thermal radiation over long timescales. But detecting such tiny differences requires next-generation instruments and highly sensitive data analysis. And then there's the cosmological question: if ECOs do exist, how common are they? Do they form from just a subset of supernovae, or are all stellar mass black holes actually ECOs in disguise? Could the supermassive objects at galactic centers, like Sagittarius A in the Milky Way, be ECOs rather than true black holes? If ECOs are a real endpoint of stellar evolution, they might be widespread. Or if the conditions required for eternal collapse are extremely rare, they might be exotic outliers. At present, the scientific community remains divided. Some physicists, particularly those concerned with quantum gravity and information theory, see ECOs as a natural and even necessary alternative to black holes. Others consider them speculative at best, unnecessary at worst, and are satisfied with the black hole model despite its paradoxes. After all, black holes are successful at explaining much of the high-energy behavior we observe in the universe. Still, the concept of ECOs continues to grow, not just because of what they solve, but because of how they challenge us to think differently. They reject the idea that nature must be abrupt, final, or destructive. They propose instead that even the most violent processes in the cosmos can be gentle in the long run, slowed by internal resistance, never quite reaching a singular end. Are ECOs real? We don't yet know. We have no direct detection, no unmistakable signal, no smoking gun. But the theory is robust. The mathematics is sound. And the questions they raise, about gravity, time, information, and the edge of physical law, are too important to ignore. Perhaps one day, with better instruments and deeper understanding, we will point to a dark object in the sky and say, "This is not a black hole, it is a star that never died." To truly understand how a star might collapse forever without forming an event horizon, we have to peer into the depths of relativistic physics, not with numbers or formulas, but with concepts that twist our everyday understanding of space, time, and gravity. What makes eternally collapsing objects so compelling isn't just the strange possibility of a star that never quite becomes a black hole. It's that this idea can emerge naturally from the core of Einstein's general relativity, when we stop simplifying and start paying attention to all the energy involved, including the energy we often overlook, radiation. In traditional black hole theory, once the mass of a collapsing object is packed within its Schwarzschild radius, gravity becomes so overwhelming that nothing, not even light, can escape. The result is an event horizon, a boundary in spacetime that forever severs the interior from the outside universe. But this model is based on a significant simplification. It assumes the region inside the collapsing object becomes empty, or vacuum-like, very quickly after the collapse begins. It's this assumption that gives rise to the clean, elegant Schwarzschild solution, an idealized, spherically symmetric black hole with no internal structure beyond the singularity. But stars don't collapse in a vacuum. When a massive star implodes, it does so in a blaze of extreme heat, pressure, and radiation. As the core gets denser and hotter, it generates more photons, neutrinos, and other particles. The surrounding material compresses and heats up too. Instead of a cold collapse into emptiness, the interior becomes a roaring furnace, packed not just with matter, but with light. Now, in relativity, radiation isn't just a passive byproduct. It carries energy and momentum, just like matter. It pushes outward. It curves spacetime. And when you include that radiation in the equations of general relativity, when you don't sweep it under the rug, you discover something extraordinary. The internal energy and pressure of this radiation begin to counteract the collapse. Not by stopping it completely, but by slowing it down. As the collapse continues, something else happens: gravitational time dilation. This is the effect where clocks near a massive object tick more slowly compared to those far away. The closer you get to the Schwarzschild radius, the more extreme the time dilation becomes. From the viewpoint of a distant observer, the collapsing surface appears to slow down, redshift, and freeze, hovering just above the event horizon, never quite crossing it. In the black hole model, this is just an optical illusion. From the perspective of the collapsing matter, the horizon is crossed in finite time, and the singularity is reached shortly after. But in the ECO model, time dilation is not just a visual effect, it becomes a physical feedback loop. As the collapse slows, radiation becomes more trapped. As radiation becomes more trapped, pressure builds. That pressure slows the collapse even more. And as the surface approaches the Schwarzschild radius, time for the collapsing material stretches toward infinity. From the outside, the object looks frozen. From the inside, the fall continues, but so slowly that the event horizon is never formed. This idea creates a fascinating scenario. An object that, by all external appearances, mimics a black hole, yet never completes its transition. Its collapse is eternal. Its surface hovers just above the critical boundary, shrinking ever closer but never disappearing. The internal structure continues to evolve, but more and more slowly as gravitational time dilation stretches every second into eternity. And here's the key: this is not science fiction. This is not a violation of relativity. This emerges directly from Einstein's equations, once we include all the physical energy sources present in a real collapsing star. When we account for the dynamic behavior of radiation and pressure, when we abandon the idea of vacuum collapse, we find a new solution to the equations of gravity, one that doesn't end in a singularity, or an event horizon, but in an endless, decelerating spiral inward. This doesn't mean ECOs are simple. In fact, they're likely very complex objects, with constantly changing internal structure, highly redshifted radiation, and interactions between matter, radiation, and gravity that evolve over incredibly long timescales. But complexity doesn't make them less real. It just makes them more like the actual universe, messy, dynamic, and governed by energy in all its forms. ECOs also fit beautifully into the emerging puzzle of quantum gravity. One of the big challenges in physics today is reconciling general relativity with quantum mechanics. Black holes, with their event horizons and singularities, create problems for quantum theory, especially with regard to how information is preserved. ECOs, by avoiding horizons and singularities altogether, sidestep those issues. They suggest a world where gravity and quantum mechanics don't have to fight, but can coexist, each limiting the other in extreme environments. And because collapse never completes, the internal energy of an ECO can, in theory, remain in contact with the universe forever. The object can radiate, albeit very faintly, and perhaps even reveal information about its interior state. In this way, ECOs offer not just a mathematical curiosity, but a philosophically satisfying alternative to black holes, an answer to the question of how the universe handles extremes without breaking its own laws. Ultimately, the physics of forever doesn't mean timelessness. It means time, stretched out to the edge of nothingness. It means collapse, slowed by its own energy. It means a star, falling into itself, never hitting bottom. As the heart of a massive star collapses inward under its own gravity, something extraordinary begins to happen. Its surface falls faster and faster, pulled toward a critical threshold in space, the Schwarzschild radius. This radius, determined by the star's mass, marks the boundary where escape becomes impossible, the fabled event horizon of a black hole. But in the case of an eternally collapsing object ECO, this threshold is never actually reached. The surface races toward it, gets closer and closer, but then slows. And slows. And slows again, inching forward ever more sluggishly, as if caught in an invisible net. Eventually, from the perspective of a distant observer, the surface appears to freeze, suspended just above that fatal radius, never to cross it. This is the eerie paradox at the heart of ECOs. They collapse eternally, yet never vanish. To understand this, we must picture the strange nature of time near intense gravity. In Einstein's theory of general relativity, massive objects warp the fabric of spacetime. The closer you get to a massive object, the more space is curved, and the more time slows down. Near a black hole, this effect becomes extreme. At the Schwarzschild radius, time dilation becomes infinite. A clock on the collapsing surface ticks more and more slowly compared to a clock far away. As the surface approaches the Schwarzschild radius, it doesn't just fall inward, it falls out of time. Now imagine watching this collapse from a safe distance, say, from a faraway spaceship orbiting well beyond the collapsing star. Initially, you see the outer layers compress and heat up. Light emitted from the surface becomes more redshifted as gravity increases. Then, at some point, the light begins to fade. Not because it has stopped, but because its wavelength is stretched so dramatically by gravity that it slips into undetectable ranges. The photons still escape, but they are robbed of their energy. The collapsing surface is still there, but it becomes dimmer, slower, and more ghost-like with every passing moment. Eventually, the collapsing surface comes within a fraction of the Schwarzschild radius. But something unexpected happens, it never crosses it. From your external vantage point, the fall appears to halt. Not abruptly, like hitting a wall, but gradually, like a ball rolling into thicker and thicker molasses. The closer it gets to the Schwarzschild radius, the more time slows down, until the object seems to pause indefinitely, frozen at the edge of darkness. This asymptotic approach, where a value gets closer to a limit but never actually reaches it, is a classic concept in both mathematics and physics. It's like chasing the horizon. No matter how far you run, the horizon always remains just ahead. ECOs operate in the same way. The surface collapses, but each successive step becomes smaller and slower. In theory, it would take infinite external time for the surface to reach the event horizon. And infinite time means it never actually happens. Collapse is never completed. This is radically different from how black holes are often described. In the black hole model, while the exterior observer sees the collapse slowing down, the object itself passes the event horizon in finite proper time, its own internal clock continues ticking. But in the ECO model, time itself is so distorted by the trapped radiation and internal pressure that the collapsing surface doesn't just seem frozen to the outside, it is actually slowed by internal physical processes. This isn't just a trick of light or perspective, it's a real, physical deceleration of collapse caused by radiation pressure and time dilation acting together. This perspective gives us a new understanding of the Schwarzschild radius, not as a point of no return, but as a gravitational boundary that can never quite be reached if enough internal pressure and energy exists to resist the final step. It becomes not a doorway to singularity, but an unreachable horizon, always receding just ahead of the collapsing surface. And there's something profoundly poetic in this image. A massive star, having exhausted all its fuel, collapses inward. But instead of vanishing, instead of being erased from the universe, it becomes trapped in an eternal process, ever collapsing, never completing. Its surface may be only nanometers above the critical radius, but that gap is enough. It's like watching a candle flicker forever without ever going out, its light dimmed beyond recognition, its surface hidden in the deepest gravitational twilight, but still there. This asymptotic behavior has huge implications. Because there's no true event horizon, the object remains in contact, albeit faintly, with the outside universe. Information and energy are not absolutely lost. The surface may still radiate, albeit so redshifted that it takes millions or billions of years to escape in meaningful quantities. But escape it can. And that single detail separates ECOs from black holes in one of the most crucial ways imaginable. It preserves the continuity of physics. And if we apply this framework to real cosmic observations, say, the supermassive object at the center of our galaxy, we're left wondering, are we really observing black holes, or are we seeing the final flickers of stars caught in a collapse that never ends? If ECOs are real, then the universe may be filled with these frozen giants, objects that appear lifeless but are still falling, still whispering, still transforming, just incredibly slowly. To the naked eye, they may be indistinguishable from black holes. But underneath, they are stars paused forever at the edge of darkness, their final act never complete, their surface never vanishing, their fate suspended on the brink of infinity. The idea of a black hole is built on a haunting certainty. Once something crosses the event horizon, there is no way back. That invisible boundary becomes a one-way membrane. Anything that enters, whether a photon of light or an entire planet, is lost to the universe forever. This is the infamous point of no return. It's a terrifying concept because it suggests that nature has places from which nothing can ever reemerge, not even information. But with eternally collapsing objects, this boundary never actually forms. And that subtle difference changes everything. In the ECO model, the collapsing surface of the star slows down as it nears the Schwarzschild radius, but it never quite reaches or passes it. As we've seen, this is due to the interplay of internal radiation pressure, gravitational time dilation, and quantum effects. Because of this, the ECO's surface remains just above the threshold where a black hole's event horizon would be expected to form. It gets closer with every moment, but in such a way that the gap between the surface and the would-be horizon never vanishes completely. It shrinks, but never disappears. So, what does this mean for escape? It means that, in theory, nothing is ever truly trapped inside an ECO, not permanently. Unlike a black hole, where crossing the event horizon cuts off any possibility of return, an ECO maintains a faint line of communication with the outside universe. The gravitational field is still incredibly strong. Time is still horrifically slowed. Light and matter still struggle to escape. But escape is not forbidden by the structure of space-time itself. It is merely rendered very, very difficult. Imagine a particle emitted from just beneath the ECO's surface. In a black hole, that particle would be doomed. It could never escape past the event horizon. But in an ECO, because there is no event horizon, that particle still has a theoretical pathway out. The gravitational redshift may stretch its wavelength to absurd lengths. Its energy may be diluted to a ghostly whisper. Its escape may take longer than the current age of the universe. But it can still, eventually, make its way back into the cosmos. This opens a stunning possibility. An ECO doesn't imprison information, it delays it. Every bit of radiation, every quantum of data, is not destroyed or hidden beyond reach, it's just slowed, delayed, redshifted beyond recognition. In this view, the ECO becomes not a tomb, but a kind of gravitational slow cooker, letting go of its contents not in an instant, but over infinite time. This also means that any infalling object, a particle, a signal, or even an unlucky astronaut, would not be erased upon crossing some irreversible threshold. The fall would be long, arduous, and cold. Time would stretch endlessly, and radiation pressure would increase. But theoretically, they wouldn't be cut off from the rest of the universe. They might even, in principle, emits signals or information that would eventually be seen, though perhaps after cosmological timescales. This has deep consequences for the laws of physics, especially in the domain of quantum mechanics. Quantum theory demands that information be conserved, that no physical process can simply erase it. Black holes, with their horizons and singularities, seem to violate this. They gobble up information and then radiate featureless, thermal noise. But ECOs offer an alternative, a cosmic system that respects quantum information, preserves unitarity, and never severs the threads that connect inside and outside. From a relativistic standpoint, this also avoids the singular warping of spacetime that leads to causal disconnection. In black holes, the event horizon marks a surface beyond which no signal can return. Causality becomes broken. In ECOs, because that surface never forms, causality remains intact, albeit stretched to the extreme. There is no firewall, no disconnection, no tearing of the universe's causal fabric. Only delay. Only distance. Only patience measured in lifetimes of galaxies. Some might ask, if ECOs allow escape in theory, why does it look like they trap everything? Why don't we see matter or radiation pouring out? The answer is in the gravitational redshift. Light emitted from near the ECO's surface is so drastically redshifted that, by the time it reaches distant observers, it carries almost no energy and takes ages to arrive. It would be like watching a movie that plays one frame every billion years. To human senses and even most telescopes, the ECO appears black, inert, silent. But from a physical standpoint, it is always just barely open. There is no cosmic gate slamming shut, only a hallway that grows longer and colder the farther you try to walk down it. This sliver of escape also suggests something profound about the nature of death in the cosmos. Black holes represent finality, a firm end where knowledge and matter both disappear. ECOs, on the other hand, are about transformation, not termination. They are an ongoing process, not a sealed result. Matter falling into them is not erased. It is slowly, gradually, transformed and perhaps eventually returned to the universe in ways we don't yet fully understand. In this sense, ECOs may better reflect the conservation principles that underpin modern physics. No loss, only delay. No barriers, only resistance. They portrayed the universe as resilient, capable of compressing, slowing, and distorting, but never of breaking the links that tie everything together. So, when we look at the dark hearts of galaxies, at the invisible monsters pulling stars into fatal spirals, we might not be seeing death after all. We might be seeing stars caught in a cosmic pause, forever collapsing but never completely closing off. And if we wait long enough, or build instruments sensitive enough, we may catch glimpses of their long, slow breath. The faint signal of an object that refuses to cross the line. The flicker of hope that, in this universe, there is no point of no return, only horizons that recede with every step. If black holes are defined by silence, by their refusal to let even light escape, then eternally collapsing objects, ECOs, represent the cosmic whisper that never truly stops. Despite their nearly indistinguishable appearance from black holes to the casual observer, ECOs possess one critical, defining difference: they may still emit light. Not in the bright, blinding flash of an ordinary star, but in a dim, redshifted trickle. A slow and continuous leakage of radiation that defies the apparent finality of black hole physics. To understand how this is possible, we have to recall a core concept: ECOs do not have a true event horizon. And because there is no sealed-off surface, the laws of physics never forbid light or other forms of energy from escaping. Instead, the structure of spacetime near an ECO makes escape exceedingly difficult, so difficult that most radiation is stretched thin and delayed into near oblivion. But difficult is not the same as impossible. Here's how it works. As a massive star collapses into an ECO, the matter at its core becomes incredibly dense and hot. Trapped within this dense environment is a sea of radiation, photons, neutrinos, and possibly even exotic quantum particles, desperately trying to escape. In a black hole, once this matter crosses the event horizon, no amount of energy can make it back out. The escape velocity exceeds the speed of light, and spacetime tilts so steeply inward that all paths lead to the singularity. In an ECO, however, there is still a surface just above the Schwarzschild radius, a surface that, while gravitationally extreme, does not mark a one-way boundary. Light emitted from this surface, or from slightly below it, can in theory still travel outward. But due to the massive gravitational pull and the extreme time dilation near this boundary, the light experiences an astonishing gravitational redshift. Its wavelength stretches, its energy diminishes, and its frequency drops as it climbs out of the ECO's gravitational well. What starts as high-energy radiation at the source, X-rays or gamma rays, may arrive to a distant observer as mere microwaves or even radio waves. That's if it arrives at all. Some of this light might take billions of years to travel just a few kilometers outward in the ECO's own reference frame. The closer it originates to the ECO's surface, the more time and energy it loses during its journey. But again, loss of energy is not the same as total loss. The signal, however faint, is still there. In fact, one of the major theoretical advantages of ECOs is that they allow non-thermal, information-rich radiation to emerge over time. Unlike Hawking radiation from black holes, which is purely thermal and appears to carry no information about the matter that formed the black hole, ECOs might emit light that retains subtle clues about the object's interior structure. That means, in principle, ECOs could let us learn something about what's inside them, if we can detect and decode the ultra-faint radiation they emit. This opens the door to some incredible possibilities. If ECOs radiate slowly over infinite time, they act almost like decaying lanterns, extremely slow-burning, long-lived beacons that persist far beyond the lifetime of any ordinary star. They could be cosmic fossils, still shedding their energy billions of years after their collapse began, slowly cooling while never truly going dark. In this scenario, the energy we receive from them wouldn't be a violent burst, but a near-eternal echo. Faint, gentle, persistent. There's also the fascinating concept of trapped radiation inside an ECO. During collapse, as the density increases, radiation gets caught within the object, bouncing around, exerting pressure, but not immediately escaping. This internal radiation supports the object against complete collapse, even as it tries to leak outward. Over time, some of this trapped energy may filter through the outer layers, eventually reaching the surface. Once there, it can begin the long climb out of the gravitational well, emerging as ultra-redshifted emission detectable only with the most sensitive instruments. This mechanism means ECOs could exhibit a form of surface luminosity, however weak, unlike true black holes. This light wouldn't come from the accretion of matter alone, but from the internal structure of the object itself. If we could detect this emission, it would be a game-changer. It would offer a way to distinguish ECOs from black holes observationally. We'd be able to say, this object is not silent. It's singing in a whisper we've only just learned to hear. Of course, detecting this radiation is an enormous challenge. For one thing, the redshift involved near an ECO's surface is mind-boggling, trillions of times greater than anything we see in normal stellar objects. The emitted photons may have wavelengths so long that they blend into the cosmic background noise. And the timescale of emission might stretch beyond the age of the universe, making real-time observation nearly impossible. But astronomers are starting to look for echoes in the data. One promising area is gravitational wave astronomy. Some researchers believe that if two compact objects merge and the result is an ECO rather than a black hole, the post-merger signal might carry unique features, faint ripples of light, or gravitational energy that appear long after the main event. These so-called gravitational wave echoes could be the first concrete observational evidence of ECOs, if confirmed. Another area is high-energy astrophysics. Some studies suggest that ultra-compact objects with surfaces, like ECOs, might emit brief flashes or bursts of radiation when infalling matter impacts the surface. A black hole, having no surface, would simply absorb the material silently. But an ECO might produce a delayed flare, as the matter crashes into the collapsing, but still material, surface and then radiates outward. If such emissions can be spotted and distinguished from ordinary astrophysical noise, they could help us identify ECO candidates. Ultimately, the possibility of light from an ECO speaks to the heart of its difference from a black hole. One is an endpoint, a dead end. The other is a process, a slow unraveling of collapse, a transformation that never finishes. Light, even in the faintest whisper, is the signature of life. If ECOs can emit light, then they are not dead. They are dying, but in a way that preserves memory, structure, and connection with the universe. And perhaps, in the silence of the night sky, some of the most ancient light we see is not from stars that exploded, but from stars that refuse to fully disappear, still collapsing, still glowing, still holding on at the edge of darkness. One of the most stubborn puzzles in modern theoretical physics, perhaps the most famous, is the black hole information paradox. It began as a subtle inconsistency in the math but evolved into a full-blown crisis at the very foundation of our understanding of how the universe works. In simple terms, the paradox is this: if black holes erase information, they violate the laws of quantum mechanics. And if they don't erase it, then something is wrong with our understanding of gravity, space-time, or both. The problem arose when Stephen Hawking showed in the 1970s that black holes aren't entirely black. They emit faint radiation, now known as Hawking radiation, due to quantum effects near the event horizon. This radiation is purely thermal. It carries no information about the matter that fell into the black hole. Over time, this radiation causes the black hole to lose mass and eventually evaporate completely. But if that's the end of the story, if the black hole disappears and all that remains is featureless heat, then the information about what fell into it is gone. Permanently. That's a big problem. Because in quantum mechanics, information must always be conserved. Nothing, not even a black hole, is allowed to destroy the unique quantum state of a system. This is a foundational principle of the theory. If black holes break it, then either general relativity or quantum mechanics, or both, must be wrong or incomplete. For decades, this dilemma has haunted physicists. But ECOs, eternally collapsing objects, offer a radical, and potentially satisfying, escape route. The key lies in their central difference from black holes: no event horizon. Since ECOs never form a true event horizon, they don't sever information from the rest of the universe. They don't have a region of spacetime from which nothing can ever escape. And without that sealed-off boundary, there's no irreversible process of information burial. In an ECO, the collapse continues endlessly, but always remains just short of completion. Radiation is trapped, redshifted, delayed, but never fundamentally blocked from escaping. That changes everything. In an ECO, matter and radiation continue to interact within the object. The surface, if we can still call it that, radiates, albeit faintly, due to intense internal energy and pressure. This radiation may carry imprints of the internal state of the collapsing object. It may be highly redshifted, deeply delayed, and incredibly faint, but it's not devoid of structure. It's not thermal noise like Hawking radiation. It carries the possibility of being information-rich. From this perspective, the information paradox doesn't even arise. Information isn't destroyed, it's slowly released. It may take millions, billions, or even trillions of years, but the information encoded in the collapsing matter is not irretrievably lost. It's just trapped in a long, slow, gravitational bottleneck. This is a crucial distinction. It means that quantum mechanics remains intact. Unitarity, the principle that quantum evolution is reversible, is preserved. We don't need to invoke wild ideas like holographic dualities, firewalls, or remnant states. ECOs provide a grounded, relativistically sound structure in which information escapes not through magic, but through relentless, patient physics. Some theorists have argued that if ECOs emit light or other radiation, no matter how weak, then the information paradox may simply not apply to these objects. The paradox is a byproduct of the assumption that event horizons are absolute and unavoidable. ECOs challenge that assumption at its root. If gravitational collapse is always slowing, always resisting, and never final, then the black hole is not a one-way gate. It's a door that slowly creaks open over cosmic time. In fact, Abhas Mitra and others who have worked on the ECO model suggest that by including realistic features in the collapse, like radiation pressure and quantum effects, the very formation of a horizon is prevented, and the supposed paradox of information lost dissolves. The information isn't destroyed. It's just incredibly slow to leave. Even more intriguingly, this means that the fundamental conflict between general relativity and quantum theory may not be as severe as we thought. If ECOs represent the true endpoint of gravitational collapse, then perhaps general relativity doesn't need to be discarded or replaced in these regimes. Perhaps it simply needs to be completed with a more realistic account of matter, radiation, and quantum energy fields. This also ties ECOs to the broader search for a theory of quantum gravity, a theory that unites the smooth geometry of spacetime with the jittery probabilities of quantum mechanics. ECOs might be a bridge between these two worlds. They obey Einstein's equations, but only when those equations are supplied with a complete and physically rich energy-momentum tensor, one that includes the pressures, flows, and feedback of radiation and quantum fields. And so, ECOs become not just an answer to a paradox, but a candidate solution to the next great unification in physics. The implications go far beyond astrophysics. If ECOs can preserve information, they suggest that the universe is fundamentally conservative. No information is ever truly erased. No quantum state ever disappears. Even in the deepest collapse, even in the most extreme gravity, the logic of the universe remains intact. That is both humbling and thrilling. It invites us to see the cosmos not as a place where death is absolute, but where transformation is never total. Where endings are only limits approached, never reached. And where the answers to our deepest questions may be delayed, but never denied. ECOs, in this light, are not just theoretical alternatives. They are guardians of information, protectors of the sacred code that underlies reality itself. In them, the universe whispers that nothing is ever truly lost, only hidden, waiting, collapsing forever, yet still connected to everything. If eternally collapsing objects, ECOs, are more than just mathematical curiosities, if they truly exist out there in the cosmos, then surely, somewhere, we must be seeing them. But here's the great challenge. ECOs, by their very design, mimic many of the external features of black holes so closely that distinguishing between them isn't just hard, it borders on the impossible using traditional observation methods. Still, astrophysicists are searching. And tantalizing clues are beginning to emerge from the data, like whispers from the edge of darkness. The first and most obvious place to look is at black hole candidates, the objects we currently classify as black holes based on their gravitational influence. These include stellar mass black holes formed from supernova remnants, and supermassive objects lurking at the centers of galaxies. In many cases, we can't see these objects directly. Instead, we infer their presence by the way they pull on nearby stars, twist spacetime, and devour gas in their vicinity. But these observations don't definitively prove that an event horizon is present. They only confirm that the object is incredibly compact, massive, and dark. That leaves the door open to ECOs. One line of inquiry involves the accretion disks around compact objects. When matter spirals into a black hole, it heats up and emits X-rays and other radiation before crossing the event horizon. If ECOs have a real, albeit collapsing, surface just above the Schwarzschild radius, then matter falling onto them would impact that surface. This could produce a faint flash or reflection, a rebound of energy that wouldn't occur with a black hole, which absorbs everything silently. Some scientists are now reanalyzing X-ray emissions from compact objects, looking for subtle signatures, like a delayed burst of radiation or unusual spectral features, that could hint at a surface rather than a horizon. Another promising area is the study of gravitational waves. Since 2015, LIGO and Virgo have been detecting the space-time ripples from merging compact objects, what we think are mostly black holes. The standard waveform of a black hole merger has a distinct signature, an initial chirp, as the objects spiral together, a peak as they collide, and then a rapid ring down, as the resulting black hole settles into a stable state. But some theorists predict that if the post-merger object is an ECO instead of a true black hole, the ring down phase might include echoes, faint, repeated reverberations of gravitational energy. These echoes would be the result of gravitational waves bouncing between the ECO's surface and the gravitational potential well surrounding it, slowly leaking outward. Unlike black holes, which swallow these vibrations, ECOs would allow them to bounce and decay. This could produce a faint, periodic pattern in the gravitational wave signal, a calling card of a surface, not a horizon. In 2016 and again in later datasets, some researchers claimed to find tentative evidence of these echoes in the LIGO data. These claims were highly controversial. Some scientists argued the echoes were real, while others said they were statistical noise. The debate is still ongoing. But with better detectors on the way, including the upcoming LISA mission, Laser Interferometer Space Antenna, and upgrades to LIGO and Virgo, our ability to detect faint echoes will improve dramatically. Another observational test comes from radio astronomy. The Event Horizon Telescope, EHT, captured the first ever image of the shadow of a black hole in 2019, the now famous picture of the supermassive object in the galaxy M87. This shadow is thought to result from light being bent by the intense gravity near the event horizon. But again, the image doesn't directly show the event horizon, it shows a dark region where light is being strongly bent or captured. If ECOs exist, they could cast similar but subtly different shadows. A black hole would produce a sharply defined, featureless dark region. An ECO, with a radiating or reflective surface just outside the Schwarzschild radius, might emit a small amount of light, or allow for light to reflect, producing a slightly brighter interior shadow or different photon ring structure. These differences are incredibly subtle, but with future EHT observations of other black hole candidates, like Sagittarius A, at the center of our own galaxy, scientists are hoping to compare the detailed light profiles with predictions from both black hole and ECO models. Additionally, ECOs may influence quasi-periodic oscillations, QPOs, observed in X-ray binaries. These are flickers of X-ray light believed to come from hotspots or vibrations in the accretion disks of compact objects. If ECOs have surfaces or emit radiation differently than black holes, their QPO patterns might differ slightly. Some researchers are re-examining archived data for unusual patterns that could indicate a non-black hole compact object at play. There's also a long-term observational strategy. If black holes truly evaporate via Hawking radiation, then over cosmological timescales, they should vanish. But if ECOs exist and radiate more slowly, or not at all, they would persist. In theory, we could search for ancient compact objects that have existed far longer than any black holes should have survived. While this is mostly a hypothetical search for now, it highlights another fascinating difference in how ECOs might stand the test of time. So far, the evidence is inconclusive. No single observation has definitively proven that ECOs exist. But no observation has ruled them out, either. And this is what makes the hunt so thrilling. ECOs are consistent with the data we already have. They could be masquerading as black holes all across the universe. We just haven't been able to spot the subtle giveaways yet. As our instruments grow more sensitive, and our models more precise, the possibility of identifying these objects becomes more real. The search for ECOs isn't just about finding a new type of star, it's about redefining our understanding of what happens to matter, energy, and information in the most extreme environments nature can produce. Perhaps, someday soon, a flicker of light where there should be none, an echo where there should be silence, or a gravitational tremor that shouldn't exist will finally give them away. And when it does, we may find that the cosmos has been filled with eternally collapsing stars all along, hiding in plain sight, just a breath above the horizon of forever. At the heart of the eternally collapsing object ECO hypothesis lies a single fundamental question: what prevents a collapsing star from forming a true black hole? After all, classical general relativity insists that if a massive enough object collapses under its own gravity, nothing, not even light, can halt its descent into a singularity. And yet ECOs challenge this view by proposing that collapse continues forever, without ever reaching completion. But for this to happen, something must resist gravity's pull, not just briefly, but eternally. That something, many theorists argue, is a subtle interplay between radiation pressure and quantum field effects, forces rooted not in matter, but in the very structure of space, time, and light itself. Let's begin with radiation pressure, a phenomenon well understood even in classical astrophysics. In the core of any star, gravity pulls inward while pressure from hot, energetic photons pushes outward. This balance is what allows stars to shine for billions of years. But once nuclear fuel runs out, that equilibrium breaks. The core collapses, triggering supernovae or the birth of neutron stars. In the Standard Model, if the collapsing mass exceeds the Tolman, Oppenheimer, Volkoff limit, around 2 to 3 solar masses, no known force, neutron degeneracy pressure or otherwise, can resist the collapse. The object should then form a black hole. But ECOs argue otherwise. According to this model, as the collapsing core shrinks closer and closer to its Schwarzschild radius, trapped radiation becomes increasingly intense. Imagine a collapsing star's interior growing ever more compact, compressing light and heat inside a gravitational trap that deepens with every passing moment. This radiation is not free to escape easily. Gravity redshifts it, bending its path and sapping its energy, but it doesn't vanish. It continues to bounce, reflect, and build pressure. This trapped radiation doesn't behave passively. It pushes back. Unlike a classical fluid, it doesn't require density to exert pressure. Photons themselves, being massless, still carry momentum. As more radiation accumulates, due to infalling matter or from the collapse process itself, the radiation pressure increases dramatically. Eventually, a delicate equilibrium is reached. Gravity continues trying to squeeze the object further inward, but the internal radiation refuses to let it collapse completely. This balance may be unstable in a classical sense, but in the ECO model, it's self-regulating. As collapse proceeds, radiation pressure becomes stronger, pushing back harder. This feedback loop leads to a kind of stalling. The surface of the object continues to collapse, but at a decreasing rate, slowed by the buildup of internal energy. Every new layer of matter that collapses and adds to this radiation pressure. Every burst of gravitational energy gets converted, not into more collapse, but into more resistance. Collapse continues, but never finishes. It's not a static halt, it's a dynamic standstill, maintained by constant adjustment between gravity and radiation. This internal feedback mechanism, based on classical thermodynamics and general relativistic energy momentum tensors, is already fascinating. But to truly understand ECOs, we must go further, into the strange realm of quantum fields and curved spacetime. Near what would be the event horizon, spacetime is stretched to such extremes that quantum effects can no longer be ignored. The vacuum of space is no longer empty, it seethes with virtual particles, fluctuations, and zero-point energy. Quantum field theory tells us that in the presence of strong gravitational fields, these fluctuations become amplified. What was once background noise becomes real, tangible pressure. One proposed mechanism is that as the collapsing surface gets close to the Schwarzschild radius, quantum vacuum polarization effects kick in. These effects are subtle distortions in the quantum vacuum due to the extreme curvature of spacetime. As the surface tries to reach the would-be event horizon, the energy density of the quantum vacuum rises sharply. The virtual particles gain energy. Their combined effects generate a quantum pressure that resists further collapse. This is not just a passive resistance, it's a consequence of gravity's own geometry backreacting against itself through the quantum fields it stirs. Some physicists, such as Abhas Mitra and others working on quantum gravitational models, suggest that quantum radiation pressure from these effects may become strong enough to prevent the event horizon from ever forming. This provides a natural way for the object to collapse ever inward, but always lagging behind the radius where a horizon would have formed. There's also the possibility of non-equilibrium quantum states, such as Bose, Einstein condensates or coherent field configurations, forming in the collapsing core. In some speculative models, these could act as exotic forms of pressure, quantum coherent matter or vacuum states that resist gravitational compression without requiring ordinary matter. These aren't mainstream ideas, but they're serious attempts to reconcile quantum mechanics with gravitational collapse in ways that preserve information and avoid singularities. The result of these intertwined effects, radiation pressure, vacuum polarization, quantum fluctuations, is a gravitational collapse that slows down as it deepens, creating an asymptotic scenario. The object grows denser, hotter, and more extreme, but never crosses the line into becoming a true black hole. Collapse becomes not an event, but a limit approached, like Zeno's paradox in physics. Every step toward the Schwarzschild radius takes twice as long, and covers half the remaining distance. It's a process without a finale. This also redefines the idea of the surface of such an object. It's not a hard shell in the classical sense. It may be a fuzzy quantum boundary, where space-time is in a superposition of geometries, and energy densities fluctuate chaotically. It's not solid, but not empty either. It's the last layer of a star caught forever in collapse, resisting with light and quantum fury what gravity demands. The beauty of this mechanism is that it doesn't require any unknown physics to get started. Radiation pressure and quantum field effects are already baked into our theories. They're just often neglected in models that focus on idealized collapse. But if we include them, we may find that gravity doesn't win after all. It gets slowed, resisted, and stalled, not by brute force, but by the universe's own subtle architecture. ECOs, then, become not objects of static resistance, but of eternal deferral. They never form singularities. They never break the universe's laws. They never shut out information or light completely. Instead, they represent a perfect balance, an infinitely slow collapse, regulated by the whisper of quantum fields and the pushback of light. In this model, a collapsing star becomes a living process. It doesn't vanish. It becomes trapped in its own becoming, balanced forever on the cusp of oblivion, defying gravity with the soft, persistent resistance of the quantum world. The idea of eternally collapsing objects, ECOs, forming in the present-day universe, emerging from the depths of massive stars or merging compact objects, is already intriguing. But now imagine the clock wound back all the way to the very beginning. The early universe, mere seconds after the Big Bang, was a furnace of unimaginable temperature, density, and energy. It was a time before galaxies, before stars, before even atoms had properly formed, a swirling, expanding chaos of fundamental particles and raw space-time curvature. Could ECOs have formed even then? And if so, could some of them still be here, ancient and undetected, as silent relics of the universe's most primal era? This isn't mere speculation for speculation's sake. The early universe provides the perfect ingredients: extreme density, gravitational instability, and violent fluctuation for the birth of compact, collapsed objects. Traditionally, this leads to discussions about primordial black holes, PBHs, hypothetical black holes that may have formed from unusually dense regions of matter immediately after the Big Bang. These objects, if they exist, are believed to range in size from tiny specks to many times the mass of the Sun, depending on when and where in the early universe they formed. But here's where the ECO hypothesis enters with a twist. What if some, or all, of these so-called primordial black holes are actually primordial ECOs? To understand how that could happen, consider the chaos of the early universe. During the first fractions of a second, regions of space experienced rapid inflation and then cooled down, leading to uneven distributions of matter. Quantum fluctuations stretched by inflation became seeds for gravitational collapse. In certain hotspots where density exceeded critical thresholds, gravity would have rapidly overwhelmed pressure, forming what appears, at first glance, to be a black hole. However, if the ECO model is valid, the physics of extreme gravitational collapse at such densities would naturally include radiation pressure, quantum vacuum effects, and field interactions that resist full collapse. In the early universe, these effects would be even more pronounced than today due to the sheer amount of energy packed into each cubic centimeter of space. This means some of these dense regions might have started to collapse, but never completed the journey into becoming black holes. Instead, their collapse could have been eternally slowed by the very same pressures and feedback mechanisms that define ECOs in modern times, but dialed up to cosmological extremes. The result? A population of primordial ECOs, ultra-dense, ultra-compact objects born not from dying stars, but from the embryonic folds of the universe itself. They wouldn't shine, they wouldn't explode, and they wouldn't have any surrounding debris to give them away. They would simply sit in the universe, collapsing ever so slowly, hidden in their own silence. If they exist, primordial ECOs could be incredibly ancient, persisting for over 13.8 billion years. And due to their small size and minimal radiation output, they could be nearly invisible to our instruments. But that doesn't mean they would be irrelevant. In fact, their implications would be profound. First, they could contribute to the dark matter problem. One of the biggest mysteries in astrophysics is what makes up the invisible mass that seems to bind galaxies together and shape the large-scale structure of the cosmos. While traditional candidates for dark matter include exotic particles like WIMPs or axions, compact objects like primordial black holes have long been proposed as possible contributors. But if ECOs formed instead, they could be playing a similar gravitational role, exerting mass and pull without emitting detectable light. Second, they might help solve the black hole information paradox from a cosmic angle. If the earliest black hole-like objects are actually ECOs, then information has never been truly lost, even since the earliest seconds of the universe's existence. These objects could be reservoirs of primordial information, locking in clues about the universe's initial conditions, quantum seeds of cosmic structure that never collapsed fully, never formed event horizons, and never cut themselves off from the rest of spacetime. Third, they could be detectable through gravitational wave echoes or lensing anomalies. As the sensitivity of our gravitational wave detectors increases, we may begin to notice subtle differences in the signals from mergers of compact objects, echoes or deviations that suggest a surface, not an event horizon. If some of these merging objects are ancient ECOs, we could be witnessing the collision of structures older than stars themselves. Similarly, gravitational lensing, where light bends around a massive object, could reveal objects that are too compact to be stars, but too transparent to be black holes. The existence of primordial ECOs could also reframe our understanding of the cosmic timeline. The standard model assumes that black holes only formed after the first generation of massive stars died, hundreds of millions of years after the Big Bang. But ECOs could have appeared within fractions of a second of the Big Bang, forming the universe's very first long-lived structures. These objects would have lived through inflation, recombination, structure formation, and galactic evolution. They would be survivors from an epoch we can barely imagine, cosmic fossils collapsing forever. Some theorists have gone further, speculating that ECOs could influence cosmic evolution in subtler ways. Could their gentle radiation, spread over eons, have affected the temperature of the intergalactic medium? Could their gravitational pull have seeded early galaxies, or influenced the web-like structure of the cosmos on the largest scales? Perhaps most provocatively, the formation of ECOs in the early universe may hint at a deep quantum gravitational principle. Maybe the universe doesn't allow true event horizons to form, not even in its infancy. Maybe nature always prefers delays to erasure, reversibility to destruction. If that's true, then ECOs are not just exotic possibilities. They are manifestations of a fundamental law that governs collapse everywhere and everywhen. And if even a handful of these primordial ECOs still exist, they may be quietly orbiting through galaxies, waiting for the day when our instruments become sharp enough to notice them. They could be drifting through the Milky Way, dark and ancient, shadows of a time when the universe was still forming its first thoughts. In the grand narrative of cosmic history, these objects might be among the oldest storytellers, locked in a sentence that never ends, collapsing endlessly but never disappearing. Time, in the presence of intense gravity, behaves in ways that seem utterly alien to our everyday experience. Near massive objects, time slows down. This is not science fiction, but a fundamental prediction of general relativity, confirmed by everything from satellite clocks to experiments on Earth. But near an object as dense as an ECO, this warping of time reaches an extreme. The closer one approaches the collapsing surface of an ECO, the slower time flows, not just for matter and light nearby, but in the perception of any distant observer. It leads to a paradoxical state of being, a collapse that never finishes, a surface that never vanishes, and a timeline stretched out toward eternity. From far away, an external observer would see the collapsing surface of the ECO slowing down continuously as it nears its Schwarzschild radius. At first, the infalling matter rushes inward quickly, its radius shrinking fast. But as it approaches the critical boundary, the distance at which a black hole would have formed, something remarkable happens. The collapse seems to grind to a halt. Not because the object has stabilized, but because time itself is being distorted so severely that progress becomes infinitely delayed. Each tick of the clock on the ECO's surface takes longer and longer to be measured by an outside observer. The object continues to contract internally, but from our perspective, the final stages of collapse take forever. This is the root of the phrase, eternal collapse. It's not that the object stops collapsing, on the contrary, it keeps evolving inward, with its internal layers becoming denser and hotter, its surface drawing closer to the critical radius. But because of the extreme gravitational time dilation, we never see the collapse complete. The closer the surface gets to the Schwarzschild radius, the longer light and information from it take to escape. The redshift grows exponentially. Photons emitted from this surface are stretched into oblivion, and their arrival is delayed by longer and longer intervals. In fact, from our viewpoint at infinity, the ECO never actually forms a black hole, even as it becomes virtually indistinguishable from one. This leads to a poetic contradiction. From the perspective of the ECO's own collapsing interior, immense processes might be happening: radiation, pressure interactions, structural changes. But to us, all of this is happening in ultra-slow motion. A second on the surface of the ECO may stretch into years, centuries, or even longer in the frame of a distant observer. If we were to stare at such an object for billions of years, we would still see it frozen, inching ever closer to the event horizon, but never crossing it. This asymptotic behavior is deeply embedded in the mathematics of general relativity. As a massive object collapses, the light it emits takes longer and longer to escape. The gravitational redshift, the change in light's frequency due to the pull of gravity, grows without bound. At the limit, the emitted light becomes so stretched out that its energy is effectively zero. In this scenario, the ECO becomes cloaked, not by an event horizon, but by time itself. It fades into invisibility, not because it has vanished, but because it has been slowed into silence. One fascinating implication of this is that the notion of a final state loses meaning. For black holes, we speak of event horizons and singularities as endpoints. But for ECOs, there is no terminal phase. There is no moment when the object is fully collapsed. Instead, collapse becomes a process that never ends. This shifts our understanding of the universe. Instead of abrupt transitions and absolute boundaries, we see smooth, infinite deferrals. Nothing finishes. Everything continues, just more slowly and more faintly. This also opens the door to a profound idea: eternal collapse means eternal time. The object continues to evolve internally, even as its external communication slows to a trickle. That means an ECO is not a dead relic. It's alive in a sense, changing, reacting, radiating, though all of this is taking place on a timeline so stretched that from our perspective, it may as well be static. The contrast between internal and external time becomes almost philosophical. From within the ECO, collapse may continue in seconds or minutes. But to us, those seconds take longer than the age of the universe to unfold. The object is eternally in the act of becoming a black hole, yet it never becomes one. It hovers at the edge of a threshold it can never cross, suspended in a gravitational stasis that masquerades as death. What's more, this effect of time stretching is not just limited to the ECO's surface. It affects all the outgoing radiation and particles trying to escape. Their journey through space-time is extended to such a degree that information from within the ECO leaks out over infinite time. And this is precisely what distinguishes ECOs from black holes. Instead of hiding their information behind an irreversible boundary, ECOs release it, slowly, subtly, eternally. In a strange way, this eternal collapse becomes a form of immortality. The ECO does not die. It does not transition into a singularity. Instead, it becomes a cosmic performance of infinite patience, collapsing forever without ever being finished. It continues to interact with the universe, but on a scale of time and energy so distorted that it escapes casual detection. This also means that the very arrow of time near an ECO becomes warped. Events that happen close to its surface are dilated to such an extent that they appear frozen from afar. And yet, the internal evolution may be proceeding normally. This leads to a bifurcation of time, internal versus external, fast versus slow, hidden versus visible. The ECO exists at the boundary between motion and stillness, change and permanence. And the implications go further. Could the universe itself contain regions of space, perhaps seated in the early cosmos, that are eternally collapsing like ECOs, existing in suspended animation? Could pockets of spacetime be moving so slowly that we never detect their evolution? Could entire civilizations or structures be hidden behind this curtain of time dilation, too slow to be seen, but still present? In the context of cosmology, this concept even hints at the idea that eternal time dilation could act as a form of cosmic preservation. Information, energy, and structure could be locked into these slow collapse zones, preserved from entropy, degradation, or destruction simply because time no longer flows the same way. ECOs offer us more than a challenge to black holes. They invite us to rethink time itself, not as a universal ticking clock, but as a fluid, elastic fabric that responds to gravity in astonishing ways. In these objects, time becomes stretched to eternity, and collapse becomes a journey with no destination. From the outside, they are frozen. From the inside, they are alive. They are stars that never end their fall. And in doing so, they never run out of time. The concept of an eternally collapsing object, ECO, does more than just challenge our understanding of astrophysics. It invites us to reflect on the nature of reality itself. If an ECO collapses forever, never crossing the threshold into black hole status, never forming an event horizon, and never halting in its fall, then it exists in a strange twilight between motion and stasis, presence and absence, process and permanence. And this leads to a haunting philosophical question: is an ECO still part of our time-based universe? Or has it fallen outside of time altogether? To begin with, it's important to recognize that time, as we understand it, is not absolute. Einstein's theory of relativity shattered the old notion of a single, universal clock ticking uniformly for all observers. Instead, time is fluid, stretching, compressing, and even freezing depending on how fast you're moving or how deep you are in a gravitational well. Near an ECO, time doesn't just slow down. It becomes almost meaningless to us. A process that, from the ECO's perspective, may take microseconds, unfolds over millennia, or more, from the vantage point of the universe outside. So what does that say about the ECO's place in the cosmos? On paper, it is still within the observable universe, and it still has a gravitational influence that reaches us. Its mass still warps spacetime. Its shadow still curves light. Its presence can still be inferred. And yet, when it comes to actual change, evolution, interaction, those things that require the passage of time, it no longer seems to participate in the cosmic dance. Its movements have become too slow to see. Its radiation, too redshifted to detect. Its voice, stretched across eternity. The ECO thus becomes something more than just an astrophysical object. It becomes a philosophical anomaly, something that exists, but barely belongs. It is visible in gravitational terms, but invisible in dynamical ones. It radiates, but the radiation takes eons to escape. It collapses, but the collapse is eternally incomplete. It participates in the universe's story, but on a timescale that removes it from all normal storytelling. This gives rise to the idea of the ECO as a star outside of time, not because it literally exists in a different universe, but because it's been exiled from ours by gravity's grip on time itself. If the flow of time is the pulse of the cosmos, then the ECO's pulse has slowed to the point of near death. It still exists, but its timeline no longer overlaps meaningfully with ours. We live in seconds, minutes, years. The ECO lives in infinities. From this perspective, the ECO almost resembles a cosmic relic, a kind of stasis chamber in space-time, preserving matter, structure, and information in a frozen process that never completes. It is not inert, but it is almost timeless. And that blurs the line between being and non-being, between existing in the present and being permanently delayed. In fact, if the universe were to end, if everything else were to unravel, the ECO's collapse might still be ongoing, incomplete even at the end of all things. This prompts a deeper reflection. Is duration essential to existence? Can an object that never finishes changing still be said to exist meaningfully, if that change is hidden behind time dilation forever? Or does the ECO occupy a kind of metaphysical limbo, hovering between states, like a thought never spoken or a story never concluded? The philosophical parallels are rich. Ancient Greek philosophers pondered paradoxes like Zeno's arrow, always in motion but never arriving. The ECO is the astronomical embodiment of that idea, an arrow loosed by gravity, flying into collapse, but forever slowed by the curvature of time, never quite reaching its target. It is a star caught in the act of dying, but never dead. A thing with no beginning of stillness, and no end of motion. Even our language strains to describe it. We say the ECO is collapsing, but not that it has collapsed. We say it exists, but its existence slips through the fingers of time like sand. It's not a snapshot. It's a process without a punchline, an eternal pause button pressed on nature's most violent event. This also raises questions about how the universe handles causality and determinism. If events within an ECO unfold on eternally stretched timelines, then the effects of those events are delayed indefinitely. Cause and effect become smeared. Actions that take place near the ECO's surface have consequences, but those consequences may take longer to emerge than the universe itself is expected to last. The ECO becomes a kind of gravitational memory chamber, storing information and processes so slow that they can never be observed, only inferred. Some might even argue that the ECO's separation from our flow of time is a kind of cosmic modesty. It holds within it the ultimate extremes of matter, energy, radiation, and curvature, but it refuses to display them in any observable way. Instead, it hides them behind layers of slow time, delayed light, and infinite redshift. It's the universe's way of saying, here lies something profound, but not for your eyes. It's also poetic. A star, once burning with light and fury, goes dark, but not in death. Rather, it sinks into a state of perpetual becoming, always about to be a black hole, never quite arriving. It is no longer part of our time. It has no climax, no final moment. It simply continues, a whisper at the edge of space-time, never finished, never fading. And if we accept that, then ECOs are more than just objects. They are symbols of potentiality, of incompleteness, of the parts of reality that are not yet written. They teach us that not everything must resolve. Not every process must end. Some things are better left becoming, not being. They are stars outside of time. And in their slow, endless collapse, they reflect the deepest truth of existence, that to exist is not always to act, or shine, or end, but sometimes, simply to endure. For over a century, black holes have stood as some of the most mysterious and captivating objects in astrophysics, regions of spacetime where gravity becomes so strong that nothing, not even light, can escape. We've accepted their presence based on compelling indirect evidence, the powerful gravitational tug they exert on nearby stars, the strange X-ray emissions from their accretion disks, the merger signals revealed by gravitational waves, and even the now iconic shadows captured by the Event Horizon Telescope. But here's the provocative question: what if we've misinterpreted all of it? What if these so-called black holes are not black holes at all, but eternally collapsing objects, objects that look nearly identical to black holes from the outside, yet differ in one crucial aspect: they never form an event horizon. This notion challenges one of the most fundamental assumptions in modern astrophysics. It doesn't reject the observational data. Instead, it offers an alternative interpretation, one that aligns with general relativity and resolves long-standing paradoxes about information loss, singularities, and the true fate of collapsing matter. And once you start peeling back the layers, the case for ECOs as the real identity of black holes becomes more compelling than it may first appear. Let's consider what we've actually observed. No one has ever seen a black hole. We've only seen the effects we expect from black holes. When we observe stars orbiting a massive, invisible object, as in the case of Sagittarius A at the center of the Milky Way, we infer that it must be a black hole because of its compactness and mass. But this inference rests on the assumption that no other object could be that massive and yet invisible. ECOs challenge this assumption by proposing an object that is just as compact, just as massive, and almost as dark, but crucially, still has a physical surface and never crosses the threshold into becoming a true black hole. In fact, from a distance, an ECO would be virtually indistinguishable from a black hole. Its gravitational field would behave almost exactly the same. The bending of light, the redshifting of nearby matter, the behavior of orbits, all would match the predictions of general relativity for a black hole up to an incredibly small margin. The difference only becomes apparent when you look closely at what happens near the would-be event horizon. In a black hole, infalling matter disappears forever once it crosses the event horizon. No light or information can escape. The singularity lies beyond a boundary that is unobservable, unchallengeable, and, in the view of many physicists, fundamentally problematic. It's a place where the laws of physics break down, where time and space become meaningless, and where information is destroyed, unless quantum corrections or speculative theories intervene. In contrast, an ECO never reaches that point. It collapses eternally, its surface approaching the Schwarzschild radius ever more slowly, but never quite arriving. There is no singularity, no true horizon, and as a result, no event beyond return. Matter falling toward an ECO would encounter an ultra-redshifted surface, a quasi-horizon, if you will, that emits radiation faintly over immense periods. Information is not lost. It's delayed, stretched, and possibly scrambled, but still in principle recoverable. That makes ECOs far more palatable from a theoretical perspective, especially in light of the ongoing debates surrounding the black hole information paradox. Now let's apply this to what we think we know about black holes. Consider the gravitational wave detections made by LIGO and Virgo. When two black hole-like objects collide, they send ripples through spacetime that we can now detect. The waveforms we've observed match predictions for black hole mergers, but only within the precision of current models. The ring-down phase, the last moments of the merger, offers the best opportunity to distinguish a black hole from an ECO. ECO proponents argue that if we could zoom in on this final phase with enough sensitivity, we might detect gravitational echoes, caused by gravitational waves bouncing between the object's interior and its surface. In a real black hole, no such echoes would occur, waves would vanish past the event horizon. But if these post-merger echoes exist, they would be the ECO's way of announcing its difference, quietly, from the darkness. The same logic applies to accretion disks. We observe matter heating up and emitting radiation as it spirals into black holes. But if the central object has a surface, as ECOs do, then some of this matter should eventually impact that surface, producing a flash or delayed signature. The challenge is that the surface of an ECO lies so close to the Schwarzschild radius, and emits such highly redshifted radiation, that this signal could be almost imperceptible. But with better instruments and modeling, we might catch it. So why haven't we confirmed ECOs? The answer may be simple: we haven't looked carefully enough. Until recently, the black hole paradigm was so entrenched that alternative interpretations were rarely explored. But now, with the rise of high-resolution telescopes, advanced gravitational wave observatories, and quantum gravity research, the ECO model is gaining traction. What once seemed fringe is starting to look like a viable contender. If ECOs do turn out to be the true nature of what we call black holes, the implications would be profound. First, it would mean that no object in the universe has ever reached a singularity, or formed a true event horizon. That alone would revolutionize our understanding of gravity, space-time, and the end states of matter. It would also suggest that the universe is far more conservative with information than we thought, that nothing is ever truly lost, only delayed. Second, it would imply that many of the mysteries surrounding black holes, like their entropy, temperature, and Hawking radiation, must be reinterpreted through a different lens. ECOs may radiate more slowly, over longer timescales, and through different mechanisms than predicted by Hawking's equations. The slow leakage of radiation from ECOs could preserve information in a way that solves the information paradox entirely, without needing holography, firewall hypotheses, or speculative quantum wormholes. Third, it would force us to reconsider how we describe the fabric of the cosmos. ECOs represent a universe that never allows perfect isolation. No matter how extreme the collapse, no region is completely cut off. There's always a way out, however faint, however delayed. This continuity aligns more naturally with the principles of quantum mechanics, where unitary evolution forbids total information loss. In this view, what we've been calling black holes for decades may simply be the shadow puppets of a deeper truth, ECOs masquerading as their darker cousins, mimicking their behaviors closely, but retaining a fundamental connection to the rest of the universe. If that's true, then the cosmos is filled not with voids of annihilation, but with stars in eternal descent, collapsing not into oblivion but into endless process. Perhaps, when we peer into the darkness at the heart of galaxies or the aftermath of violent mergers, what we're really seeing is not the end of matter, but the beginning of a new understanding, an understanding that the most extreme objects in the universe are not finish lines, but question marks, reminders that not everything collapses into silence. Some collapse into eternity. The scientific world thrives on debate, and nowhere is that more evident than in the ongoing discourse surrounding eternally collapsing objects, ECOs. While the concept has steadily gained attention in theoretical circles, it remains a contentious and polarizing topic among physicists, astrophysicists, and cosmologists. The controversy stems from more than just differing interpretations of data. It reflects a deeper conflict about the nature of science itself, whether to accept tried and true models that work phenomenally well, or to push the boundaries in search of something that may resolve the contradictions hiding beneath the surface. Mainstream science has, for decades, embraced the black hole model as the final stage of gravitational collapse. General relativity, supported by a wealth of observational data, paints a consistent picture. When a massive star exhausts its fuel, nothing can halt its collapse beyond a certain threshold, and an event horizon forms, cutting off the interior from the external universe. This paradigm has successfully predicted the behavior of quasars, X-ray binaries, and even the shadows of supermassive objects captured by the Event Horizon Telescope. It has aligned with gravitational wave signals from merging compact objects. It has even woven itself into speculative models about the early universe and extra dimensions. But for ECO proponents, this neat picture hides uncomfortable paradoxes. They argue that the standard black hole model, while mathematically elegant and observationally efficient, glosses over some of the deepest unresolved issues in theoretical physics. Issues like the black hole information paradox, the formation of singularities, and the apparent breakdown of causality. In their view, a true scientific theory should not simply accept singularities, places where the laws of physics collapse, as inevitable. Instead, it should search for models that avoid them entirely. This disagreement is not merely technical, it is philosophical. Mainstream black hole theorists often accept that certain mysteries, like information loss, may be resolved through quantum gravity or yet undiscovered mechanisms. ECO advocates, however, push for immediate conceptual alternatives. They assert that models like the ECO don't require speculative quantum gravity theories or violations of unitarity. ECOs are conservative in a radical way. They stick closer to general relativity's core tenets while bypassing the need for singularities or event horizons altogether. One of the central figures in this debate is Abhas Mitra, a theoretical astrophysicist who has spent years developing and advocating for the ECO model. He argues, controversially, that black holes with event horizons are a mathematical abstraction, not physical reality. Mitra suggests that gravitational collapse always stalls asymptotically due to the intense radiation pressure that builds up near the Schwarzschild radius. His claims have been met with resistance and, at times, outright dismissal from mainstream physicists. Critics argue that his derivations rely on specific coordinate choices or that they conflict with the accepted understanding of general relativity. And yet, Mitra is not alone. A growing number of researchers are exploring alternative models like gravastars, fuzzballs, firewalls, and ECOs, all of which challenge the traditional black hole framework in various ways. These models share a common goal: resolve the contradictions of black hole physics without giving up consistency with quantum mechanics. Some argue that the real issue isn't whether ECOs exist, but whether black holes, as defined by their event horizons, can exist at all without violating other foundational principles. The friction between these camps becomes most evident in academic publications and conference presentations. While some journals have been receptive to ECO-related research, others are more cautious, often requiring exceptionally rigorous mathematical backing or more direct observational relevance. This skepticism is not unjustified. After all, extraordinary claims require extraordinary evidence. And ECOs, by their very nature, make extraordinary claims. Much of the debate boils down to observational indistinguishability. ECOs, by design, mimic black holes so closely that telling them apart using current telescopes and instruments is nearly impossible. Detractors argue that if ECOs cannot be empirically distinguished from black holes, then invoking them adds unnecessary complexity, violating Occam's razor. Proponents counter that theoretical soundness matters just as much as empirical distinction. If the black hole model demands accepting information lost in singularities, then perhaps it's less parsimonious than it seems. Moreover, technological advancements are beginning to shift the conversation. Gravitational wave astronomy, still in its early stages, is one of the most promising frontiers. If gravitational wave echoes or deviations from expected ring-down profiles are detected, they could provide strong evidence for ECOs. This possibility has sparked fresh debates. Some physicists claim to have detected hints of these echoes in LIGO data, though others dispute the statistical significance of those findings. As the data improves, these discussions are likely to intensify. Even within the ECO community, there's disagreement about the precise nature of these objects. Are they held up by quantum pressure? Radiation feedback? Are they semi-classical? Do they involve quantum gravity corrections? This diversity of models adds to the confusion, and for some critics, undermines the coherence of the ECO concept as a whole. But defenders see it differently. ECOs are not one thing, but a family of possibilities, all motivated by a shared skepticism of the black hole's finality. Then there's the cultural dimension. Black holes have become not just scientific objects but cultural icons, mystical, terrifying, and awe-inspiring. From science fiction to documentaries, they represent nature's ultimate endpoint. To challenge black holes is not merely to dispute a physical theory, it's to question one of the most enduring narratives in modern science. That carries weight. It makes the ECO debate not just a battle of equations, but of ideas, expectations, and imagination. Despite the controversy, the conversation around ECOs is valuable, perhaps essential. It forces scientists to re-examine assumptions, sharpen definitions, and probe the limits of theory and observation. Whether ECOs eventually replace black holes or not, they have already contributed to a broader, richer landscape of possibility, one where gravity doesn't have to end in paradox, and where collapse might mean transformation rather than destruction. As the next generation of instruments, like the Laser Interferometer Space Antenna, LISA, or next-gen EHT arrays, come online, the ability to probe near-horizon physics will improve dramatically. And with it, the debate may shift from theoretical speculation to observational clarity. Until then, the question remains open, and the controversy continues. Are black holes the ultimate truth of gravity, or merely shadows cast by something deeper, something eternally collapsing, but never vanishing? Proving the existence of eternally collapsing objects, ECOs, is one of the most tantalizing goals in modern astrophysics, not just because it would overturn decades of black hole doctrine, but because it would confirm that nature may be more elegant, reversible, and informationally complete than we ever imagined. But therein lies the challenge. ECOs are designed to be nearly indistinguishable from black holes in their external behavior. Their gravitational fields mimic those of black holes so closely that, without extremely precise instrumentation and analysis, they appear functionally identical. Yet, nearly is the operative word. ECOs differ from black holes in subtle but measurable ways, if we know where and how to look. The question isn't whether ECOs could be differentiated from black holes in principle. It's whether we can do it in practice. Fortunately, thanks to rapid technological progress in both observational astronomy and theoretical modeling, the answer is shifting toward yes. One of the most promising avenues for detecting ECOs comes from gravitational wave astronomy. When two massive compact objects spiral into each other and merge, events now regularly detected by LIGO and Virgo, the resulting gravitational wave signal contains three distinct phases: the inspiral, the merger, and the ring down. The final phase, the ring down, occurs when the newly formed object settles down into its final state, releasing characteristic vibrations that are a fingerprint of its identity. In a traditional black hole merger, this ring down follows a smooth and predictable pattern. But if the merged object is an ECO with a surface just outside the would-be event horizon, gravitational waves could bounce off that surface and reflect back into spacetime, creating echoes in the signal. These echoes would be delayed and significantly weaker than the main waveform, but they would carry crucial information. They would imply that the object has a surface, not an event horizon. Several teams of physicists have claimed to find hints of these gravitational echoes in LIGO data, particularly following the massive binary black hole mergers detected in recent years. While these findings remain controversial, some say the signals are within the noise threshold and not statistically significant. The debate itself has sparked intense interest and innovation. Future gravitational wave observatories, such as the Einstein Telescope, Cosmic Explorer, and especially the Laser Interferometer Space Antenna, LISA, will have far greater sensitivity and frequency range. These tools could either decisively confirm or rule out the existence of post-merger echoes, and with them, the existence of ECOs. Beyond gravitational waves, another path toward distinguishing ECOs lies in electromagnetic observations, particularly through high-resolution imaging of compact objects. The Event Horizon Telescope, EHT, has already provided us with the silhouette, or shadow, of the supermassive black hole candidate at the center of the galaxy M87. This shadow is consistent with the predictions of general relativity for a black hole, but not uniquely so. ECOs, due to their immense compactness and high redshift, can cast a similar shadow. However, there may be subtle differences in the brightness profile or photon ring structure, the thin, bright circle formed by light orbiting very close to the compact object. In ECOs, since there's no event horizon, some radiation can escape from the surface, even if redshifted to extreme degrees. This could, in theory, produce slight fluctuations or emissions that differ from a true black hole, where nothing escapes past the event horizon. With better angular resolution and dynamic imaging, technologies currently under development by the EHT team and its future successors, we may be able to observe these nuances. Then there's the question of accretion behavior. Black holes surrounded by accretion disks, rings of hot, swirling gas, often emit high-energy X-rays and gamma rays due to the intense friction and heating of matter spiraling inward. In a black hole scenario, this matter disappears beyond the event horizon, ending its journey. But in the case of an ECO, matter falling inward would eventually strike the surface, however compact and redshifted, and could, in principle, produce a delayed but observable radiation burst or persistent emission. Detecting this difference is incredibly difficult, because the surface of an ECO lies so close to the Schwarzschild radius that the infalling matter would appear to stall from our viewpoint due to time dilation. But with precise timing of X-ray reverberations, or modeling of disk dynamics, we might pick up on these delayed signatures. One particularly interesting observational tool in this context is reverberation mapping, a method that tracks how light from the innermost regions of an accretion disk reflects and echoes off nearby structures. If there's a hard surface, as in an ECO, instead of a horizon, it could create measurable time lags and emission signatures that subtly differ from black hole predictions. Again, this requires incredibly sensitive instruments, but the upcoming Athena X-ray Observatory and Lynx missions could provide just that. We can also look toward pulsar timing. Pulsars, rapidly rotating neutron stars that emit beams of radiation, can serve as incredibly precise cosmic clocks. If a pulsar orbits a massive compact object that is actually an ECO, its timing data could reveal minute deviations in gravitational redshift, frame dragging, or orbital dynamics. These tiny variations, imperceptible under current instrumentation, may become accessible with the Square Kilometre Array, SKA, an enormous radio telescope array under construction that promises to revolutionize precision astrophysics. On the theoretical side, developing more robust ECO models is essential. Different flavors of ECOs, such as gravastars, boson stars, or Planck stars, have slightly different predicted observational signatures. To distinguish them from black holes, we need precise, falsifiable predictions based on solid physics. This is where numerical relativity simulations come in. By simulating ECO mergers, accretion flows, and radiation patterns using supercomputers, researchers can build a library of expected behaviors to compare against real-world data. Even more futuristic are concepts like quantum interferometry and space-based horizon spectroscopy, which aim to detect quantum-level fluctuations near the compact object's boundary. If the near-horizon region of a compact object emits a faint thermal spectrum, as predicted by some ECO models, then detecting it would be a direct blow to the classical black hole paradigm. Lastly, the cosmological impact of ECOs might become observable on large scales. If ECOs were common in the early universe, as some speculate, their slow-release radiation over cosmic time could subtly influence the cosmic microwave background, CMB, or the temperature and ionization state of the intergalactic medium. These effects would be faint and diffuse, but they might help reconcile unexplained anomalies in cosmological observations. In sum, proving ECOs exist is not impossible. It's a matter of resolving small deviations with great precision. It's the astrophysical equivalent of spotting the difference between two identical twins who wear the same clothes, walk the same way, and talk the same way, but one has a secret they're hiding beneath the surface. With the next generation of observatories and detectors, we are fast approaching a time when the secret may finally be revealed. And when it is, we may find that what we once thought were black holes, cosmic graves from which nothing returns, are in fact something far more mysterious, more elegant, and more enduring, stars that never stop collapsing, never seal their fate, and never quite leave the universe behind. When we first heard the deep cosmic hum of gravitational waves in 2015, it marked the dawn of a new era in astronomy. Suddenly, we weren't just seeing the universe, we were listening to it. These ripples in spacetime, produced by titanic mergers of compact objects, have opened a new window into the most extreme environments in existence. But as our instruments sharpen and our data pools grow, a new and profound question is emerging. Are we truly hearing black holes, or something else entirely? Could the signatures we interpret as black holes merging actually come from eternally collapsing objects? And if so, would their gravitational wave patterns reveal their true nature? To understand how ECOs might emit different gravitational wave signatures than black holes, we must first revisit how gravitational waves are generated. These waves are created when massive objects accelerate, and few events are more violent and dynamic than the inspiral and collision of two compact stellar remnants. The resulting signal can be broken down into three phases: inspiral, merger, and ring down. During the inspiral, two massive objects circle each other, slowly losing energy to gravitational radiation. This part of the signal is relatively well understood and consistent for any compact object of a given mass and spin, whether it be a neutron star, black hole, or ECO. That's one reason why, so far, the early stages of detected gravitational wave events have matched predictions for black hole systems so well. However, the differences emerge in the final stages, specifically the ring down. In a traditional black hole merger, the two objects collide and fuse into a single black hole. The resulting object is not immediately calm, it oscillates, vibrates, and sheds deformations in the form of gravitational waves. These waves fade over time in what's called a quasi-normal mode, a predictable, exponentially decaying waveform. Crucially, once the event horizon forms, any further disturbances are swallowed, and the emission ends quickly. But in the case of ECOs, the story is different. Since ECOs do not possess event horizons, their surfaces are capable of interacting with gravitational waves. This difference has a dramatic consequence. Instead of terminating the waveform at the ringdown, ECOs may exhibit late-time gravitational wave echoes. Here's how it would work. After the merger, gravitational waves would not simply vanish into a horizon. Instead, they could reflect off the ultra-compact ECO's surface, bounce around in the intense gravitational well, and eventually escape again. These delayed waves would emerge as a faint but repeating series of echoes, tiny ripples following the main ringdown, each weaker than the last. This echo pattern is one of the most sought-after fingerprints of ECOs. To visualize this, imagine shouting into a canyon. With a black hole, the canyon swallows your voice entirely. With an ECO, the canyon is nearly bottomless, but still has a wall that reflects sound back up to you, slowly, faintly, but definitely. Detecting such echoes is no easy task. They are expected to be highly redshifted, delayed by milliseconds to seconds depending on the mass of the object, and orders of magnitude fainter than the main signal. But if we can find them, there would be compelling evidence that what we call a black hole is instead something stranger, something that collapses forever, but never quite disappears. And this isn't just theoretical speculation. Multiple teams of researchers have claimed tentative evidence for echoes in the LIGO and Virgo data. In some cases, the timing and structure of these echoes have roughly matched predictions from ECO models. However, the results are controversial, with skeptics arguing that the apparent echoes could be artifacts of data processing or statistical noise. The scientific community remains divided, but intrigued. Beyond echoes, there are other subtler differences in the gravitational wave signatures of ECOs. For example, the ringdown frequencies and damping times of an ECO may slightly differ from those of a black hole with the same mass and spin. The absence of a true event horizon and the presence of a reflective or partially absorptive surface could modify the vibrational spectrum of the final object. These deviations might be tiny, but they could become detectable with next-generation observatories. The upcoming LISA mission, a space-based gravitational wave detector with arm lengths millions of kilometers long, will be especially sensitive to the low-frequency signals produced by supermassive ECO mergers. LISA could, in theory, catch the elusive echoes that Earth-based detectors miss. Its unparalleled sensitivity and long observation times may allow it to resolve differences in ring-down modes that ground-based detectors like LIGO and Virgo can't currently discern. Even beyond LISA, proposed observatories like the Einstein Telescope and Cosmic Explorer promise significantly enhanced sensitivity to high-frequency gravitational wave signals. These could offer the precision necessary to distinguish the fine structure of gravitational waveforms, and potentially confirm whether echoes, shifts in damping rates, or deviations in quasi-normal modes are real and consistent with ECO models. There's also theoretical work being done to model the gravitational signatures of different ECO types. Some models predict resonances or quasi-bound states that may create unique spectral features in the gravitational wave signal. Others suggest that certain ECOs may produce nonlinear memory effects, where a persistent distortion in spacetime remains after the wave passes, a kind of gravitational scar that may carry telltale clues. And this opens the door to machine learning and AI in gravitational wave analysis. By training algorithms on both black hole and ECO merger simulations, researchers can develop pattern recognition tools that detect even the faintest anomalies in real signals. These tools could sift through thousands of waveforms to find the rare ones that carry the echo or deviation signature, signals that human eyes or traditional statistical models might miss. In the end, gravitational waves could be the Rosetta Stone for understanding ECOs. Just as the spectrum of light revealed the secrets of atoms, the spectrum of gravitational waves may reveal the secret inner structure of the universe's most extreme objects. We're still in the early stages of this journey. The symphony of spacetime has just begun, and we are only learning to hear its harmonies. If ECOs are real, and if they do announce themselves through gravitational wave echoes or spectral fingerprints, it will be a revolution, not just in astrophysics, but in our understanding of matter, time, and the fate of the cosmos. It would mean that even in death, stars don't disappear. They sing. Quietly, slowly, but forever. At the deepest levels of our physical understanding, two giants reign supreme: general relativity, which describes gravity and the structure of space-time, and quantum mechanics, which governs the behavior of particles, fields, and all things microscopic. Each is incredibly successful in its own domain. General relativity elegantly explains the motion of planets, the bending of light around stars, and the dynamics of entire galaxies. Quantum mechanics, on the other hand, predicts with astonishing precision the interactions of subatomic particles, the behavior of atoms, and the fabric of matter itself. And yet these two pillars of modern physics are not compatible. Nowhere is this incompatibility more glaring than in the heart of a black hole. General relativity predicts that inside a black hole lies a singularity, a point of infinite density where time and space collapse into nothingness. But infinities in physics are red flags. They signal that a theory has reached its breaking point. And indeed, quantum mechanics rebels against this notion, demanding that something, some hidden layer of physics, must take over before the singularity forms. This is the core motivation behind the search for a theory of quantum gravity, a framework that unites the geometric beauty of relativity with the probabilistic precision of quantum theory. It's in this crucible of paradox that eternally collapsing objects, ECOs, emerge as a compelling alternative. Not only do they offer a gravitational solution that avoids the formation of singularities and event horizons, but they also serve as a conceptual bridge to quantum gravity, an object born in classical gravity but seemingly infused with quantum behavior. ECOs challenge our assumptions about collapse, causality, and the finality of death in the cosmos. In doing so, they act like a testbed for the next layer of physical law, a place where quantum corrections may prevent gravitational breakdown without invoking the full machinery of a quantum gravity theory. In this sense, ECOs are more than just alternatives to black holes. They're the physical expressions of a deeper philosophical shift, one that refuses to let gravity operate in a vacuum, independent of the quantum world. Instead, they suggest a soft landing for collapsing matter, not an abyss, but an eternal dance just shy of catastrophe, stabilized by subtle but persistent quantum pressures. Many candidate theories of quantum gravity naturally produce ECO-like outcomes. Take loop quantum gravity, LQG, for instance. In this framework, spacetime is not smooth and continuous but quantized, made up of discrete loops of gravitational field. At extremely small scales, near the Planck length, LQG predicts that gravity may become repulsive, creating a kind of pressure that prevents total collapse. This quantum bounce can halt the formation of singularities and lead to stable, ultra-compact objects that resemble ECOs in behavior. These objects may radiate, collapse ever more slowly, and hover forever just outside the Schwarzschild radius. Then there's string theory, which replaces point particles with vibrating strings in higher dimensions. In this context, some black hole analogs may not be black holes at all, but fuzzballs, dense configurations of strings and brains that replace the classical idea of a singularity. Fuzzballs don't have event horizons in the traditional sense. Instead, their surface is a tangled mess of microstates that can still interact with the external universe. Sound familiar? The fuzzball picture is strikingly similar to ECOs, both in their lack of a true horizon and their potential to radiate and preserve information. This connection isn't accidental. ECOs, fuzzballs, gravistars, Planck stars, all these exotic alternatives to black holes represent a theoretical convergence. Different quantum gravity frameworks, though built on different assumptions and mathematical tools, often lead to non-singular, horizonless compact objects. These models differ in detail, but they share a philosophical core. Gravity alone is not the end of the story. At some critical density, quantum fields push back. Another fascinating concept comes from asymptotically safe gravity, a lesser-known but powerful approach in which gravity remains well-behaved at all energy scales due to a special fixed point in its renormalization group flow. In this theory, the very geometry of spacetime evolves with scale, and the strength of gravity might effectively weaken at extremely small distances. This could halt the collapse of matter and allow stable ECOs to form instead of singularities. Again, the key idea is that quantum corrections tame gravity without needing to abandon general relativity entirely. Yet another connection arises in noncommutative geometry, a mathematical model where the fabric of spacetime itself doesn't behave like smooth coordinates, but like a quantum operator, with built-in uncertainty and fuzziness. These properties naturally limit how tightly matter can be packed, leading to compact objects that, again, resemble ECOs. What makes ECOs especially intriguing in the context of quantum gravity is that they can be approached from both directions. From the general relativity side, you can derive ECOs as solutions to Einstein's equations with energy-momentum components that include trapped radiation or anisotropic pressures. From the quantum side, you can derive similar behaviors from loop corrections, string microstates, or modified propagators. This dual derivability gives ECOs a kind of theoretical flexibility. They're not bound to a single framework but appear as recurring solutions across diverse approaches. This versatility makes ECOs an ideal proving ground for the quantum gravity frontier. They allow theorists to test ideas about unitarity, causality, entropy, and spacetime topology without requiring a full, working quantum gravity theory. They invite a subtler form of unification, not by merging equations, but by reframing collapse itself as a phenomenon that bridges the classical and quantum worlds. And then there's the role of ECOs in addressing the black hole information paradox, which sits at the very heart of the quantum gravity disconnect. If black holes evaporate via Hawking radiation and truly have event horizons, then information is lost, a direct violation of quantum unitarity. But if black holes are actually ECOs, then there's no event horizon, and information can escape, albeit slowly and heavily redshifted. This removes the paradox entirely, and restores harmony between gravity and quantum mechanics. In this light, ECOs could be seen not just as objects, but as manifestations of a deeper consistency, evidence that the universe doesn't allow singularities, that information is never truly lost, and that no region of spacetime is ever beyond reach. Perhaps most profound of all, ECOs hint that collapse is not a terminal process, but a transformation. What we once thought were the graves of stars may instead be laboratories for quantum gravity, a place where the cosmos writes equations in fire and curvature, but never crosses the line into finality. We're standing at the edge of a great synthesis. Whether it's loop theory, string theory, or something not yet imagined, ECOs invite us to believe that the bridge between general relativity and quantum mechanics isn't built in equations alone. It may already exist out there, in the heavens, collapsing forever but never gone. Deep at the center of the Milky Way, in the heart of our galaxy's gravitational well, lies an object of immense power and mystery, Sagittarius A. For decades, astronomers have gazed into this swirling abyss, observing the strange and violent behavior of stars whipping around an invisible mass over 4 million times the weight of our Sun. They've marveled at the X-ray flares that burst from the galactic core, the eerie radio silence punctuated by brief outbursts, and most recently, the haunting shadow revealed by the Event Horizon Telescope. All signs point to the same conclusion, that Sagittarius A is a supermassive black hole. But what if it isn't? What if this cosmic behemoth isn't a black hole at all, but rather an eternally collapsing object, hiding just beyond the reach of observational certainty? What if, instead of being a region of spacetime from which nothing can escape, Sagittarius A is a nearly collapsed star, still radiating, still evolving, still visible in theory, if only we had the precision to see it? This possibility is not just a speculative alternative. It could rewrite everything we think we know about the galactic core, gravity, and the very nature of cosmic death. To entertain this idea, let's first consider what we do know about Sagittarius A. Using powerful telescopes like Keck and the Very Large Telescope in Chile, scientists have tracked the orbits of stars like S2, which race around the invisible object at breakneck speeds. The tightness and shape of these orbits tell us that the central mass must be incredibly compact. Whatever it is, it must fit within a space no larger than our solar system. Moreover, its mass, about 4.3 million solar masses, must be packed into that small volume without any obvious surface radiation. All this is consistent with a black hole. But consistency is not proof. And that's where the door opens to ECOs. If Sagittarius A is an ECO, it would still produce the exact same gravitational influence on surrounding stars. The orbital motions we observe, those stunning elliptical dances, would be virtually identical whether the object is a black hole or an ECO. That's because at distances far from the core, the gravitational field of an ECO is indistinguishable from that of a black hole with the same mass. This is a fundamental feature of general relativity, the no-hair theorem, which states that the external field of any spherically symmetric mass is determined solely by its mass, charge, and spin, regardless of what's inside. So, Sagittarius A could be hiding in plain sight, looking every bit like a black hole to our current instruments, yet fundamentally different in nature. In the ECO scenario, Sagittarius A isn't an object with a true event horizon, but a surface hovering just above the Schwarzschild radius. Matter falling toward it would appear to slow down and redshift, never quite disappearing. From our vantage point, that matter would seem to freeze in time, but unlike in a black hole, it wouldn't vanish behind a point of no return. Instead, over extremely long periods, it might re-radiate its energy back into space, subtly altering the radiation environment of the galactic center. This brings us to one of the key differences that might help distinguish Sagittarius A as an ECO, the presence of delayed emissions or gravitational echoes. If Sagittarius A has a physical surface, no matter how compact and redshifted, then matter crashing into it could, in principle, generate faint, ultra-delayed light or gravitational wave signals. These echoes would be vanishingly difficult to detect, but not impossible. Theoretically, high-precision infrared or X-ray telescopes could look for reverberation signals or flickering patterns that don't align with standard black hole accretion behavior. In fact, some anomalies have already been noted. For instance, quasi-periodic oscillations (QPOs), strange flickers in the X-ray emissions from around Sagittarius A, have puzzled astronomers for years. While QPOs are generally attributed to dynamics within the accretion disk or relativistic precession, some have proposed that they could also hint at resonances between the surface of an ECO and the infalling matter. That is, the light we're seeing could be echoing, not from empty space, but from something just beneath the Schwarzschild threshold. Additionally, the flaring activity of Sagittarius A remains one of its most mysterious behaviors. Roughly a few times a day, this normally quiet object emits sudden bursts of infrared and X-ray radiation. The energy involved is massive, and while black hole models can explain some of it via magnetic reconnection in the disk or sudden influxes of material, ECO models offer another possibility: material hitting the ECO's surface and rebounding. In a black hole, such energy would vanish beyond the event horizon. But in an ECO, it could generate transient radiation, short bursts that, while heavily redshifted, would eventually escape into space. Then there's the matter of Hawking radiation, which should cause black holes to very slowly evaporate over time. For a supermassive black hole like Sagittarius A, this process would be effectively unobservable. It would take longer than the age of the universe to radiate even a single proton's worth of energy. But ECOs may not follow this rule. Since they lack an event horizon, they are not subject to the same irreversible entropy conditions. Instead, they could emit standard blackbody radiation from their surfaces, albeit extremely redshifted and minimal. Over time, this could alter the thermal balance of the galactic center in subtle ways. What about gravitational waves? Could they offer clues? If Sagittarius A were to merge with another compact object, say, an infalling stellar mass black hole or ECO, the resulting gravitational wave signal could, in principle, carry the signature of ECO physics. Instead of ending in a clean ringdown as in a traditional black hole merger, the waveform might include late-time echoes or modulations due to reflections off the ECO's surface. While no such merger has been detected near Sagittarius A to date, the LISA mission, launching in the 2030s, may be sensitive enough to detect such events, especially if they involve intermediate mass objects spiraling into the core. Another line of evidence may lie in the surrounding plasma and magnetic fields. ECOs, with their physical surfaces and radiation dynamics, might interact differently with the chaotic magnetic fields at the galactic center. This could influence the polarization of emitted radiation, the structure of jets, if any, or even the heating of nearby gas. Advanced radiopolarization studies, like those already being conducted by the Event Horizon Telescope, may uncover discrepancies between what we expect from a black hole and what we actually observe from Sagittarius A. Perhaps the most exciting aspect of this speculation is philosophical. If Sagittarius A is an ECO, then the center of our galaxy is not a place of finality, but of ongoing process. It is not a tomb, but a stage of evolution that continues indefinitely. This challenges the prevailing narrative that black holes are dead ends in space-time. Instead, ECOs suggest that the cosmos doesn't simply allow infinite densities and irreversible collapse. It fights against them, in subtle ways, through radiation, quantum effects, and the resistance of the fabric of spacetime itself. It also forces us to confront our cosmic bias. For decades, astronomers have interpreted every compact, massive, dark object as a black hole by default. But what if this assumption is premature? What if ECOs are not just theoretical curiosities, but the rule, not the exception? What if we've already seen dozens, even hundreds, of ECOs, and mistaken every single one of them for black holes? This raises a final and humbling possibility, that we are surrounded by immortal stars, collapsed in form but never extinguished in essence. That Sagittarius A, long believed to be a one-way abyss, is in fact a mirror, showing us the limits of our current knowledge. A silent reminder that nature may hide its truths not behind walls, but in nearly invisible edges, where collapse slows, light lingers, and time never quite gives up. As we peer deeper into the cosmos, cataloging black holes of all masses, stellar, intermediate, and supermassive, we do so under an assumption so pervasive that it's rarely questioned, that all these invisible giants are black holes. We assign that label to any object with high mass, tight gravitational influence, and no visible surface. But what if this assumption is wrong, not by a small margin, but in a fundamental way? What if the universe is not filled with black holes, but with eternally collapsing objects, each one a star that has never truly died? It may sound radical, but there's growing reason to believe that ECOs might not be rare anomalies, but rather the default end state of gravitational collapse. If this is true, it would mean the universe is filled not with countless silent voids, but with an entire population of slowly radiating, nearly frozen stars, hiding just beyond the edge of visibility. They would resemble black holes in almost every way, but only almost. And that difference, infinitesimal though it may be in terms of space-time curvature, could alter our understanding of stellar evolution, galactic formation, and even cosmological history itself. First, consider just how many supposed black holes we've identified so far. In our galaxy alone, estimates suggest there could be 100 million or more stellar mass black holes. Most of these are invisible. Only a few dozen have been observed directly through X-ray emissions or gravitational interactions. The rest are inferred statistically, their presence deduced by missing mass or orbital anomalies. In recent years, gravitational wave detectors like LIGO and Virgo have added dozens more to the list, each identified by their mass and the waveform signature of their merger. But what if these are ECOs? Gravitational waves from compact mergers, as previously discussed, are not necessarily unique to black holes. ECOs, lacking an event horizon but still ultra-compact, can generate nearly identical signals, except perhaps in the final ring-down, where echoes or slight timing differences might emerge. In most cases, especially with current detector sensitivity, those differences are lost in the noise. So in practice, every time we say, black hole merger, we may actually be observing an ECO event. And if even a fraction of these are misidentified, then ECOs could already be as common as black holes, or more. Then there's the realm of supermassive black holes. Nearly every galaxy has one at its center, ranging from millions to billions of solar masses. We've observed their gravitational dominance, seen the flaring of accretion disks, and even photographed their shadows. And yet none of this directly proves the existence of an event horizon. Shadows can be cast by ultra-compact objects without a horizon. Accretion behavior can be mimicked by ECOs. Flares and emissions can be explained by infalling matter interacting with a surface, however deeply redshifted. Indeed, some researchers argue that ECOs may explain certain observational puzzles better than traditional black holes. For example, the brightness variability of certain active galactic nuclei, or the unusual radiation patterns of X-ray binaries, might make more sense if the central object had a surface rather than a vacuum. The flickering, the lags, the odd timing structures, they all whisper of interactions that shouldn't exist in a true black hole. And then there's cosmological implications. If ECOs are a natural consequence of gravitational collapse, then they should have formed not only in stellar deaths but also in the early universe, potentially giving rise to primordial ECOs, objects born in the dense fog of the Big Bang, too small to form by stellar processes but too dense to remain stable without collapsing. These could be the missing link in understanding dark matter, or at least a significant fraction of it. While black holes are considered thermodynamically dead, except for their infinitesimal Hawking radiation, ECOs may be slowly radiating, constantly in the process of collapse, but never quite finishing. This makes them dynamic, living, in a sense, and could allow them to interact with the cosmic environment in ways that traditional black holes cannot. Over billions of years, their emitted radiation, though feeble, could subtly alter the interstellar medium, seed magnetic fields, or influence galaxy evolution. This idea also brings us face to face with the startling realization: if ECOs are common, then the life cycle of stars is far more complex than we believed. Instead of ending in a final, singular collapse, the death of a massive star might enter an endless phase of collapse, a process that is never complete, always evolving, always changing, though at timescales so vast we may never witness more than a fraction of it. It's not death. It's suspension. We might already be seeing hints of this in systems like GRS 1915+105, a microquasar whose peculiar X-ray variability and timing structures have challenged standard black hole models for decades. Some have speculated it may host an object with a surface, something like an ECO. Likewise, certain tidal disruption events, where stars are torn apart by supermassive compact objects, have shown unexpected emissions that could point to a reflecting surface rather than an absorbing horizon. The implications are staggering. If the cosmos is filled with ECOs, then we must re-express the cosmic census. Every model that uses black holes as endpoints, stellar population models, galaxy formation, the cosmic matter-energy budget, would need re-evaluation. ECOs, with their ability to slowly radiate and potentially preserve information, would not just change astrophysics. They would transform our understanding of entropy, causality, and time. And then there's the philosophical implication. A universe of ECOs is not a graveyard, but a slow-motion symphony, where collapse becomes a kind of eternal stasis. These are not monuments to destruction, but to endurance. They are stars frozen in the act of death, preserved like insects in amber, radiating ever so faintly into the darkness. We look into the sky and see the past, the ancient light of stars long dead. But in the depths of space, there may be a different kind of memory, not light, but collapse, not brightness, but resistance, not disappearance, but the soft and infinite slowing of time. ECOs may be the most elusive relics of the cosmos, not because they're hidden, but because they look exactly like what we expect, until we listen more closely. And so the next time we hear the roar of merging giants across the cosmos or image the silhouette of a monstrous shadow in a galaxy far away, we must ask, are we seeing death? Or are we witnessing a new phase of cosmic existence, forever collapsing, never gone? In the silent heart of a distant galaxy, beyond the reach of visible light, a star once lived. It was colossal, burning bright with nuclear fire, fusing elements in its core while flinging waves of radiation across space. For millions of years, it was a beacon, a forge of heavy elements, a sculptor of surrounding gas, a centerpiece of its stellar neighborhood. But as all stars do, it exhausted its fuel. Its brilliant flame dimmed, its outer layers swelled, and gravity, patient and relentless, began to reclaim its dominance. Collapse began. Not with a bang, but with a silent implosion deeper than sound. Layers upon layers of matter folded inward, gravity squeezing space and time into tighter knots. By all accounts, by every equation and every astrophysical model, the star should have ended in the most absolute of fates, the formation of a black hole. A singularity. An event horizon. The point at which time halts, and no light escapes. And yet it didn't. Because just as it approached the edge of that infinite fall, something happened. Or more precisely, something didn't happen. The collapse didn't finish. The surface didn't cross that invisible line. Time slowed, exponentially, infinitely, from the outside perspective. Radiation, trapped within, fought back. Quantum fields fluttered with resistance. Gravitational collapse, thought to be inevitable, found itself halted, not abruptly, but asymptotically, like a heartbeat fading into stillness but never silencing completely. The star became an eternally collapsing object, a cosmic chrysalis. Not a black hole. Not a singularity. But something in between, the dying breath of a star stretched into eternity. From far away, it looks no different than a black hole. Light curves around it. Time dilates near it. Stars orbit its gravity as though it were a perfect shadow. But unlike a black hole, it still has a surface, an invisible veil, mere fractions above the Schwarzschild radius, forever approaching but never breaching the boundary of no return. It is a surface that never fully forms, yet never disappears. In this object, we find the star that never truly died. Its collapse is its existence. Every passing moment draws it infinitesimally closer to the event horizon, but it never arrives. The infalling matter continues to spiral inward, its journey frozen in time from the viewpoint of the outside universe. To any distant observer, the star is paused in its final act, caught in the climax of its gravitational descent. And there it will remain, for billions upon billions of years, or longer than time itself can measure. It is not death. It is perpetual becoming. This object is not extinguished, but enduring. It does not vanish, but hides, like a whisper too soft to hear, yet echoing eternally in the fabric of space-time. Its surface radiates, ever so faintly, with energy barely escaping the grip of its own gravity. Its presence bends light, commands stars, and shapes galaxies. And yet, it exists just outside of certainty, beyond what we can truly detect. It defies entropy's erasure and the singularities' collapse. It may be the universe's most subtle rebellion against finality. If we think deeply, perhaps this isn't just an astrophysical oddity. Perhaps it's a message, written in the geometry of the cosmos itself. That not all collapses end in destruction. That some endings are infinite transformations. That in the darkest corners of the universe, there is still motion. Still process. Still story. What we once called black holes may, in truth, be these ever-fading stars, stars that carry memory, that trap light not behind a wall, but beneath a veil. They are the survivors of collapse. The remnants of radiance that fold inward forever without breaking. They are stars whose death is not a moment, but a journey. One so long and so slow that it transcends our understanding of time. So as we look out into the void and name these shadows black holes, perhaps we are naming them too soon. Perhaps they are not endings, but eternal pauses, sustained by a balance we have only begun to grasp. In this final reflection, the ECOs stands not just as a scientific model, but as a poetic truth. The universe, ever mysterious, does not always choose annihilation. Sometimes, it chooses a quieter path, a collapse without conclusion, a fade without a fall, a silence that sings over eons. And so the star, once bright and burning, continues. It collapses, but it lives on. Forever. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.